Good morning, everybody. Welcome to the fourth annual SCaLE container track for SCaLE for all things containers. We're now the containers and orchestration track. We used to be the containers and virtualization track, but people stopped submitting virtualization talks. I'm told people still do virtualization. How many people here still work on overt VMware? Yeah, that hasn't gone away. So, just if you want to submit a virtualization-based talk next year, we might take it. Just letting you know. I'm one of the three track chairs. The other two being Elizabeth Joseph and Stephen Wong. Stephen could not be with us for the obvious reasons. You'll see Elizabeth later on today. We worked really hard to bring you a balanced set of content covering all bases, only to have our efforts entirely smashed by a little microscopic studded ball. So one of the things I want to say today is a lot of the speakers that you'll see today and Saturday and Sunday were swapped in at the last minute, were people that I knew who had talks, and I said, this person canceled because work has suspended all business travel. Could you possibly do a talk about this? So I am going to ask you to be extra generous with your applause and forgiving of any preparation issues that anybody has, because a lot of the speakers you're seeing today may have found out that they were doing a talk at SCaLE 48 hours ago. But we will do our best for you, and we do have a full track today going all the way until 5 p.m., covering a lot of different things around containers and orchestration. So for our first talk, to give you a broad overview of understanding where we're all going with this, we're going to have Karen Brunner, who's going to talk to us about Kubernetes as a concrete abstraction layer. Karen is an expert in Disney, Warner Brothers, and Aesop's fables, and irresponsibility.
Can everybody hear me?
Yep. No. Try it again.
Try again.
It might be the mic is just too far from your mouth.
Oh, I do hear noise. Is that better? Is that good?
Check.
I'm talking. Can you hear? All right, let me adjust it. Let's see. Will that hold? Closer? Is that good? Is that good?
Okay.
Does everybody hear me in the back?
Yep.
In the front? In the middle? Okay.
Yay.
Thank
Okay,
you.
well, welcome, Karen.
Thank you. And if unfortunately I do not have the excuse of being one of those people who only had 48 hours knowledge. I had a month or so, but I did finish my slides about 48 hours ago, so there you go. So I have a long history in I started out as a Unix system and going to the DevOps, system engineer, whatever, SRE track. I am finally no longer on call. I am sorry? A little louder? Okay. Is that better? No. Okay. Is that good? Is that better? Not better? I can speak louder. Oh, there we go. I just have to hold my hand like this the whole time. Is that good? Okay. Sorry about that. Okay. So after decades literally on call, I recently became the technical evangelist at the company I'd been working at. StackRox, we do Kubernetes security. There is my plug, because they're paying for my trip. I am a totally sane cat lady. And on Twitter, and I'll post the links to the slides afterwards on Twitter and on LinkedIn, my Twitter handle is FuzzyKB. So obviously I have to talk about what is Kubernetes. Who here has actually at least touched Kubernetes, maybe? Pretty much, okay. Who here actually works with Kubernetes in production? Okay. Who here is running Kubernetes on different platforms, like either multi-cloud or on-prem? And okay. So obviously they'll tell you it's a container orchestration platform, which, you know, if you sit there and try to explain that to your grandma, is probably not going to fly. So this is what I think Kubernetes actually is, or at least what it feels like. It's kind of like a self-driving car for containers and workloads, but you know, it's not completely self-driving, and you get in different cars, stuff doesn't work the same, and if it catches fire, it burns for hours. So in this talk specifically, we will cover, and there are a lot of pictures of my cats, in this case, this cat likes blanket forts. We'll talk about the Kubernetes release cycle and the conformance program, and then we'll talk about where the differences lie, which include storage, service load balancers, node lists, security options, a couple other differences, and more importantly, what you can kind of do to plan for these differences so that your applications can just be very portable. You don't have to craft custom manifest for every single application you deploy. So the Kubernetes release cycle, they release every 3 months at any time, because the releases, at any time they'll have 3 supported versions. Oh, I can hold, yeah, that may work better. It's a little awkward. Okay. Is that better? Okay. Let me get untangled now. Okay. Okay. I don't know. Okay. So I have no idea what's going on. Okay. So Kubernetes, they release every 3 months. At any time, they have 3 supported versions. There has been a proposal to support 4 versions, and so be a full year of support for a version instead of 9 months like it is now. We'll see. It probably won't happen for the next release, but it's in discussion. And they have this really cool, if you haven't seen it before, there's this really cool interactive site for their release notes. So you can actually tune in, you know, you can do a bunch of different searches. You can say, I want security-related releases, any security features that came out or bug fixes that came out in Kubernetes 1.15 or 1.16. So definitely relnotes.k8s.io is really useful to visit if you're trying to figure out what's supported in the version you happen to be running. This is the current support matrix just for the big 3 providers compared to vanilla Kubernetes. As you can see, everybody's on the default of 1.14, which is not actually supported by Kubernetes Foundation at this point. And interestingly enough, GKE was the last of the 3 to make 1.14 the default, which happened, I think, 1 or 2 weeks ago. And it's also interesting that Azure, AKS, is quickest to bring out the preview versions. So, CM, the Cloud Nation Computing Foundation is a governing body for Kubernetes. They have a conformance program, so you can make your flavor whether you're hosting managed Kubernetes or whether you're creating a tool that will install unmanaged Kubernetes. They have a set of standards so that you can run these tests and say, hey, yes, I conform to everything. But it only covers parts of Kubernetes. Kubernetes is meant to be, it's very opinionated in its core functionality, but it's meant to be also very extensible, very customizable based on your needs, your actual hardware or cloud environment, and a lot of other factors. So that's the main reason we see differences between different providers. So the things that are covered under the conformance test are the kubelet behavior. And the kubelet is that process that runs on every node, and it's responsible for talking to the API server and saying, oh, I'm supposed to schedule this pod, and it needs these things. And containers come up, they have the right volumes mounted, and that sort of thing. And then it garbage collects everything. That's all covered by the conformance. Most core API resources are covered. The core resources are the bits you play with, like the config map, pods, secrets, namespaces, the building blocks. It also covers the app API resources, and these are built on the replication controller, on the pod replication controller. So these are deployments, daemon sets, stateful sets, batch API resources, jobs, cron jobs. These are not service-oriented containers. These are containers pods that do something and then exit. They're expected to have a ephemeral limited lifespan. And this also covers the standards for pod-to-pod and service networking. Any pod should be able to directly address any other pod without dealing, and even if the virtual routing, it goes through proxies or whatever, but the pod should just know I can talk to this other pod at this address and not have to worry about it. And then the service, how the virtual IPs for the services actually work. So the things this doesn't cover are storage class and persistent volumes, because those are very dependent on what's available to you in what platform. Services of type load balancer, again, this is an externality that's, you have to support what you're in, and core Kubernetes can't really address that. So you should be allowed to, if you have the right drivers, if you have everything in place, use whatever load balancer is available. Any APIs that require, for the most part, plugins, most controllers, or any kind of device drivers, for obvious reasons, not covered. And also, this is coming up more and more nodeless Kubernetes platforms. So as an example, like I said, lots of cats. We cover, pods are covered, load balancers, not. So some examples. I ran a bunch of tests. These are the evaluation environments I used. I used the defaults for everything, with a few exceptions. AKS, you have to choose between KubeNet or the Azure Container Network Interface. I chose KubeNet. And for COPS, I chose the Flannel CNI because kubelet, you kind of need a VXLAN to work really well in AWS. And I didn't want to use, I would usually go to Canal if I had a choice, but I didn't want to just plug in network policies for a reason. Again, all of these are defaults. For obviously the first three are the cloud-hosted platforms. The latter three are self-managed. And I put them all on AWS as kind of a comparison just to see how even different providers that are using the same cloud infrastructure, basic cloud infrastructure, can differ. So we'll start with persistent volumes. These are storage that you have multiple options for storage. You can just do a local, what ends up being either a local directory on the node, or it's scratch space. So it's not stateful. If your container dies, data goes away. The node goes away, data goes away. So you provision an external disk from whatever service you have that can give you disk space. And persistent volume, if a pod dies and a pod comes up to replace it, it will move and follow that pod if everything works properly. So you define what kind of back-end storage you can use by using storage class, the storage class resource. And there's usually a default that's set up by every provider or every installer. But even these have some differences. So EKS, you bring up, you ask for storage, and it gives you GP2, which is their basic solid-state drive-backed storage. But in Azure and in GKE, they give you, the default is hard drives. And obviously, there's going to be a performance difference there, which you may not expect. Both AKS and GKE have standard solid-state drive options, but you just have to know to choose them. And if you want to make your apps portable, you probably want to change the default class so it's consistent across providers. COPS and OpenShift deployed on AWS also use GP2 solid-state volumes. Kubespray by default doesn't. The installer supports everything. Kubespray is really portable. It's really nice it'll run on pretty much, it supports almost any platform, and including on-prem, direct to hardware, so it's very flexible that way. But it leaves, even on consistent platforms like known platforms like AWS, it still leaves the job of actually dealing with the controllers, setting up the cloud-aware controller to the user. That's why there's nothing by default. It can be made to, you just run the standard AWS cloud controller, and it will magically work, in theory. So, like I said, one way to make this more predictable and make your persistent storage more predictable, use standard default storage classes. If in every environment you have the option between solid state and hard drives, pick one, whichever works best for your organization, pick one and make that the default storage class. But you can also then create other storage classes that are optional, like maybe you want the default to be solid state, but for slower workloads where they just don't need the throughput, use hard drives. But just make them available, make it a separate optional storage class. Avoid provider like the special Snowflake offerings. These are vendor specific, much more vendor lock-in. Thinking of things like Amazon's Elastic File System, which a lot of providers just don't have. It's their NFS implementation, hosted NFS. Most providers don't have an NFS implementation, and then also you'd be using NFS. And okay, some people just like to do that. I don't know. I don't anymore. You also have the option of running something like Ceph. Ceph is it's consistent across platforms because you use. You set up a cluster with node attached or host attached storage, and it manages doling out the volumes. And Rook is an interface that can run over Ceph. It's a lot of overhead, both in hardware or virtual hardware and in operations. But if you want really a consistent interface wherever you run, it's going to create a storage abstraction layer so that Kubernetes doesn't. You're not breaking the Kubernetes abstraction layer when you hit storage. So that's one option that's more portable. But again, it's a lot more work to set up and manage. So next we're going to talk about service load balancers. These are also defaults. Again, a lot of cloud providers have a lot of different classes of load balancer, but they all act differently and they all choose different defaults. So the biggest thing, probably one of the most important differences is whether or not the source IP is preserved when it gets to the client. So if you have an internet-facing service and you want to know what IP address your client is from, either for audit purposes, for firewall purposes, or just to track where your users are, you would like to have the source IP. You'd like to tie it to a specific request. You also care about the idle timeouts. This can matter for a number of reasons. If you're doing a lot of gRPC, you would rather have longer idle timeouts. So Azure deploys their standard load balancer. And again, I just have a service manifest. I don't have anything special about it. It's just type load balancer. It will give you an Azure standard load balancer, which will preserve the source IP. It will do source netting. Their defaults, it's not, I don't think it's their standard. Okay, the standard default, and I've already forgotten this number. This number is either the standard for the load balancer in general, but I think AKS load balancers have a different default. Nope, I didn't write it down. But it's tunable. You can do anything from 4 to 30 minutes. EKS in Amazon, it gives you a classic elastic load balancer. This does not preserve the source IP. Default timeout 60 seconds. You can do anywhere from 1 to 4,000 seconds. GK uses their external TCP UDP network load balancer, and it does preserve the source IP, and I could not find any documentation about the idle timeout. It may be there. I dug, I couldn't find it. COPS and OpenShift, I'm not sure if OpenShift uses the standard AWS Cloud Controller, which is the piece that lies between Kubernetes and your actual infrastructure and manages provisioning, whatever you need. But I assume they do because they seem to default to the same behavior. They both, COPS and OpenShift, will by default give you a classic elastic load balancer. So differences in load balancers. One thing you can do in your service manifest is set external traffic policy to local. And this means that so service routing in Kubernetes by default, kube proxy sets up a round robin routing if you have multiple backends for the same service. And it's, by default, it's just totally random. Even if the request comes into a node with a pod for that backend service, it's random if it'll hit that one or another one. This setting external traffic policy to local will force it to serve from a pod on that node. And if there is no pod on that node that responds, it just drops the connection. So you want to do one of two things. You either want to make sure your load balancer is doing health checks, so it's only routing these requests to nodes that can serve this, that have the pod so that they can serve this request, or use a daemon set, which will put the pod on every single node. So your load balancer must support source NATing. Otherwise, it can't get the source IP. It's lost somewhere else. And if you have a load balancer that doesn't have source IP NATing, you can either check to see if your provider offers different load balancer types, or you can use, some of them support proxy protocol, which adds a string at the beginning of the request, but your application has to be aware of that. It has to be looking for that. It has to know it's going to get the proxy protocol header and be able to consume that. So usually you change the load balancer behavior by adding annotations to your service manifest. And these vary completely, for the most part, by cloud provider. So for an example, in AWS, you can use a network load balancer, which will preserve the source IP. It's just not standard. So you would add this annotation, AWS load balancer type, network load balancer, NLB. If you still want to use the classic ELB, but you want to use proxy protocol, and the classic ELB only supports proxy protocol v1, that's good to know. You can add an annotation for that to enable proxy protocol data on every single request. So I have a quick demo that may or may not be completely functional, but we'll see. And now I have to type with the microphone. Okay. Okay. I will try to, let me make the font bigger. I'm going to put this down for a minute. I have two terminal windows. I'm going to run this on Azure AKS, and this is the first column. Second column will be Amazon EKS, and then third column is GKE. So I just set up a really simple front-end demo. It's got an Nginx pod, simple service, and let me start tailing these logs. So you can see, obviously some of these have requests already. Okay. So this will work. So I'm getting the public IP for each of these front ends, and I'm just gonna, it's simple, plain HTTP, and this is what should happen. But you can see the last line, this is a private, go ahead. You can't see, let me make it a little bigger. Okay, this is, you can see these are private RFC 1918 requests, or IP addresses. So these are coming from generally within the VPC or within the cloud provider. Same here, same here. Plane. Okay, so now I'm going to set the external traffic policy to local on each of these. So this is a quick, it doesn't have to change, the change happens totally in the queue proxy on the nodes, so it doesn't have to reprovision or change anything on the load balancer. So it's quick, it's quicker than I can type. Ooh, can't type. So now if I curl, it will hopefully give me, oh yay, hey, that's an external IP address. However, if I do this in AWS, hey, I still get the same private IP address. It does not preserve the source IP. And then over to GKE, did I cut and paste it? Maybe I have a firewall issue. Okay, it may not come up. It will give me the public IP address if it works. So we can try. I didn't have any success. Unfortunately, I set most of this up last night, and I did not have any success getting the NLB annotation to work, because I didn't do that until this morning. We can see if it works better now. But I also set up a different service facing, or service with the back end. Oh, here's the IP address. Oh, hey, GK came through. Look, same public address. Actually, it's this one. Oh, hey, yeah, the NLB did finally come up, and it gives me the right IP address. So you can see here I have these two services. One is Nginx, which is standard, and then I created with the same backend labels, but a different service resource, which you can do. You can have multiple services that use the same backend with a network load balancer. And again, those are just using the annotations. So I just added the annotation for the AWS load balancer type. Okay, so that was my quick demo. Okay, so next we're going to talk about nodeless Kubernetes. This is pretty new. The open source, I wouldn't call it a standard yet. There are no standards around this yet. But one of the most popular, it's an implementation, but you have to still adapt it to whatever provider, whatever environment you're in. It's the Virtual Kubelet project. They are currently, so there are two issues here. For one thing, there is no conformance standard for nodeless Kubernetes. And also, nodeless Virtual Kubelet or any other implementation is probably not going to be conformant. The Virtual Kubelet team tested their implementation against the Kubernetes conformance test, and it's about 70%. The biggest standard portability issue is that there is no daemon set support. And the daemon set, again, it puts a pod on every node. But obviously, if you're just provisioning a virtual node to run one pod, you can't really do that. The problem, so that's this is a core functionality that's expected for Kubernetes, and obviously it just doesn't apply. It's not going to apply. Cloud providers are jumping on nodeless for a large degree. In AKS, it uses Azure Container Instances, and their implementation is based on Virtual Kubelet. EKS on Fargate, which was a big deal to some people when it was announced last December at reInvent, is not based on Virtual Kubelet, but probably not coincidentally, it shows a lot of the same behaviors. And GKE doesn't actually have a true nodeless. They have Cloud Run, which is actually under the hood the Knative function as a service. But even if you're using hosted Cloud Run, there's no direct interface. You could probably wrap it and make it act like nodeless, but they don't have support for that, at least right now. So common limitations for these managed providers, at least comparing AKS and EKS. As I said, no daemon set support, but that's going to be pretty standard. You cannot run privileged containers, and this is any kind of privilege, whether it's running the container as root, giving it host or network or process space access, anything, and especially not network admin capabilities. And the obvious reason is these are multi-tenant, and not just you multi-tenant like a Kubernetes cluster, but AWS customer base multi-tenant nodes. You can't mess with that. And the problem with not having privileged containers, things like, even if you have a daemon set, say you're just doing it for pod monitoring or log collections, you can make it a sidecar in your pod and it will still work. But if you're using a network policy provider or a service mesh like Istio, those are expecting generally to modify the IP table rules on your node so that traffic does what it's supposed to do. those are not available. They will silently not work. I don't know about Istio if you have a service mesh, how that, I assume that it just can't be seen. It's not going to certificate, it's not going to handle things properly. But network policies will just silently fail for that pod, even if it's part of a service, and even if it's talking to node, depending on the direction of the network policies. And unless you're looking for it and you mitigate for it, you may not know that's going to happen. You also have no node level monitoring visibility, which for security, you really want to be able to have, use something like eBPF tracing. You want to be able to see what service calls, what processes your containers are actually spawning, because if they are somehow, a bad image, they're compromised, whatever, the container is going to lie to you. You really won't need to see the operating system kernel to see what's going on, and that's not available. You kind of have a very fuzzy idea, but it's, for very strict security, it's not really a good option. So next we're going to talk about standard Kubernetes security features. What's on by default, what's available. RBAC is role-based access control is, if you're running Kubernetes and you're not using RBAC enabled and actually defining roles, please stop. It's pretty standard by this point. It's either optional or always on at this point in most providers. EKS is always on, and you can say, oh, hey, EKS is secure, but I think they just always turn it on because they don't want to have to manage. You have to enable it as a flag to the API server, and I think they just don't want to have flags that they either enable or disable, so it was easier just to turn it on always. And OpenShift it tends to be, they work very hard to be more secure by default, so it is also always on there. Otherwise, it's optional but enabled by default at this point on the other providers and on COPS and Qspray. Network policy. This is how you're going to firewall your pod-to-pod traffic. Create rules about who can talk to what and who can't talk to what. It's optional in AKS, and there's a caveat. Both RBAC and network policy. When you have to turn these on when you create your Azure Kubernetes service cluster. You cannot turn it on later. So you really want to plan these clusters out, and if you're in AKS, because they introduce a lot of features that are also, you want to use them, you have to enable them at creation time, I would just, automate a way to migrate your workloads when you want to create a new cluster to use a new feature. EKS, it's user managed, by which I mean they have instructions for installing Calico. User applies the YAML themselves and is responsible for all upgrades. GK, it's also optional, but you can enable it whenever you want. And they actually manage upgrades and everything else for you. You don't have to run any YAML, apply any YAML files. COPS, COPS and Qspray, it just depends on what network type you choose. Both of them, by default, Qspray uses Calico, so it's on by default. COPS does not. COPS uses KubeNet by default, so you would want to either choose a different provider altogether or install Calico manually. And OpenShift, they actually, this is a recent, I think it probably started with 4.1, I don't know for a fact, but they used to prefer their own network segregation until I think the 4.1 release. So now network policy, though, they've moved to make that the default, and it's optional, you can turn it off, but it is, because you might want to have the legacy, their legacy policy, you might want to keep using it, but it is now enabled by default. And they do not support pod security policy. Pod security policy is, it's actually, there's been talk for a while, they're going to deprecate it, but they just haven't figured out what they're going to replace it with. So this is, pod security policy lets you set certain conditions. It will not admit pods that, say, want to run as root. You can set something like that in the pod or container security context. You can require that they use a specific UID. You can prevent them from doing any kind of privilege escalation. It's a little tedious to manage, and it's very limited in what it does let you control. So it's optional in most providers, and it's always on in EKS again because you have to run it. You have to enable it with an API server flag, and I don't think they want to make any of those user configurable. other areas where you're probably going to see problem areas. So there are different types of Kubernetes admission controllers, and admission controllers are optional pieces of software that you can plug into the request handling pathway. So the API server, the Kubernetes cluster API server will get a request, and it says, oh, for this type of resource, I need to send it to this admission controller or this list of admission controllers. And there are a lot of different admission controllers, but the two that are probably most interesting to users are the validation webhook and mutating webhook. And the validation webhook is nice. It just says, I got a request of type pod, and I want to make sure, again, sort of this is what pod security policy does, although it doesn't, it has its own admission controller. It just says, oh, this you can have a rule that says, oh, hey, this container wants to run its root. No, reject it. So the API server just refuses to create that. And then mutating admission controllers are a little more interesting, although they're also more dangerous. You can say something really simple like, oh, every pod that gets deployed in this namespace should have a label saying it's deployed in that namespace. Or it should, you can, so it'll add the label for you. You can, if you program the admission controller, it will add the label for you. Say you want to, oh, hey, you're running Istio, and you want to inject the sidecar. That's exactly what the Istio sidecar injector does. It just, so that users don't have to change their deployment or pod manifest. It just gets every request for a pod and say, well, this namespace, Istio is enabled, puts another container in there that runs the proxy. Pretty much anything you can change or add or do to any kind of resource, mutating webhook can do. So security around those, even more important than validation. But there are also a lot of other smaller admission controllers. Those two, though, are going to be the ones that, especially if you're programming or you want some kind of standard, those are going to be the most interesting to you. Another difference are the enabled feature gates in Kubernetes. So a lot of features, especially when they're beta, you have to use a feature gate to turn them on. But even afterwards, even after they go to GA, it depends. I think they usually, I'm not sure if they always remove the feature gate or they just leave it for a while and leave it on by default. Anyways, so especially when a managed provider is releasing a new version of their managed platform based on a new version of Kubernetes, a lot of times they will disable even really desirable features by default just because they're not ready for them or they're not ready to test them completely. They're trying to preserve some kind of backwards compatible behavior maybe. So you kind of have to dig sometimes. You have to read a lot of release notes and make sure everything is doing what you need it to be doing. Some of them will even offer different enabled API groups. Again, as long as they offer that standard set and support it and it behaves correctly that we saw earlier, that's fine. But some of these are optional. So you can do kubectl API resources, and it will show you what API resources are enabled on your cluster. And it's less likely, but even different container runtimes can affect some very low-level changes. Mostly, the main differences, though, this is fairly standard. It's probably going to be in the allowed capabilities. These are Linux-level capabilities like netadmin or privileged or other. I'm blinking on the list, but netadmin is probably the biggest, most widely used in most cases. So these are less some of these are less likely to cause issues, but I think EKS, for example, was kind of late to the game in allowing mutating admission controllers, mutating webhook admission controllers. So they just turned it off, and it's very useful. It makes not having it makes, like I said, something like Istio, which is going to want to inject a sidecar. You can manually do that, but then you're manually adding it. So these are also, if you're using very new features, something you really need to look at for portability. So we saw for specific examples some way to maintain portability. Generally, making sure your clusters are consistent. There are some higher level things you can do. Some of these are nicer than others. You can just create self-managed clusters using a tool like Kubespray, or even to some degree OpenShift abstracts a lot of this. Kubespray, though, supports a lot more platforms, but it does leave a little more of the customization work to the user. And it really needs better installation instructions. Yeah, it's a lot of well, you run this command and then stuff happens and now you have a cluster. And it's like, I don't think that's how do I, okay. So Sonabui is the tool that is used to get official, if you want to make your Kubernetes distribution officially conformant, you run Sonabui with a flag, so it'll run the plugin. Sonabui was originally created by Heps.io, so now it is part of VMware. It's nice, you can create your own plugins though that have certain tests. So what happens, you run it, you run the Sonabui command against a cluster, it creates a lot of pods and subpods, and it can take a long time to run. It's running a lot of tests, it can get very deep. I think it was just in Kubernetes 1.17 that earlier they promised that you could run the conformance test and not break anything, but now they don't make that promise, because they just want to run deeper tests. You're not going to run this against a production cluster, you're going to run it against a standardly configured cluster, but without production workloads. So it spits out a big file in XML, because who doesn't love XML, with all your test results. And it's very long, but I suggest try it out one time, see what's tested, see what's not tested. It does group the conformance test with their standard end-to-end test, so you just have to grep out the end-to-end. But you can also write your own plugins, stuff you care about, and it can be either core or not core. But what do I want these clusters to do? What standard functionality do I need them to have so I can make sure that my app can run on any of these platforms? Make sure, not just for good security, although definitely for good security, that you're enabling RBAC and network policy everywhere. This has two effects. It's good practice, but it also means you can just keep your manifest, all of the manifests for every piece of your component together, and they're standard, and you're not cookie cutting, you're not saying, oh, well, this cluster doesn't get a network policy, just apply them. And there is a weird thing about RBAC and network policy, and I'm like weird in that it's bad. So the resources are standard, so they will generally, if you do that kubectl API resources list, they'll show up. And you can create those resources, and the API server is super happy to create those resources for you. However, unless there's a controller that's running that's actually paying attention to these resources, they may not apply. They will just, and if there's not, they will just silently, fail. That's not good. So test anytime you create a new network policy, anytime you create a new role binding or cluster role or whatever, test it. Test both positive and negative tests. Can I still run this? Can I not run this thing that I'm supposed to do? Can I not connect to this pod that I shouldn't be touching? And again, use consistent resource manifests across all your platforms. Make sure they're portable. You're still going to do a bunch of Go templates probably, but try to minimize that because it's easier to manage. And you want things to be, if you really want your environment to behave as much as possible in the same way wherever you run it, make sure it's defined the same way. And so you don't have a bunch of different files. And I've seen horrible if then Go templates and you don't know what's going to happen. You want to keep them as readable as possible. It's going to make maintaining them and understanding what they're going to do much, much, much easier. Like I said, pod security policy is probably going to go away soon. Well, maybe not soon. Again, they don't really know yet what they're going to replace it with. One possibility is the Open Policy Agent Gatekeeper. It's an admission controller. At this point, it's just validating. I think there are roadmap plans to make it mutating too, but right now it will validate. Again, I want to create a pod that does this, and it will go through its criteria and say yes or no. it's getting a lot of traction. It's getting a lot of attention, but it has a very high learning curve to configure correctly because you're writing both OPA's Rego language, and you're also it creates a lot of custom resource definitions. In fact, you create a rule, and then you create a custom resource definition to apply that. It's complicated. So it may or may not be the standard. There's some simpler admission controllers. But one of the nice things about OPA is that you can limit it by any field, pretty much any attribute to any resource type. So pod security policy, again, it has a very narrow set of fields which you can evaluate on. OPA Gatekeeper, it's pretty much, if it's in the manifest, you can say yes or no based on the value. So it's infinitely configurable, but with that it's complicated. You can also just write your own admission controller if you only care about a few things. But again, you're going to have to test it, you're going to have to maintain it, make sure it does the right thing and doesn't do the wrong thing. So I have a very long list of references. First off, I want to thank Brendan Cox, and I'm going to mispronounce his name, Madhuri Hachuri, for answering my questions about Virtual Kubelet on the Virtual Kubelet channel on the Kubernetes Slack workspace. There's not a lot of documentation. And in fact, I first asked them, and I think I reached out to them 2 weeks ago asking about it, and they're saying, oh, Brendan is literally checking the conformance test right now. We'll get back to you. And they were nice enough to get back to me with that. Virtual Kubelet is 70% compliant with Kubernetes conformance. They're also, I assume the work will start also defining what the standard, I don't know if they're going to guide it or they'll leave it to the conformance say, but at some point they're going to have to define what should a nodeless platform do, what are these basic set of common functionality and features that these platforms should have. Because, like I said, right now you can't really predict. They do seem, both because of the nature of the nodeless environment and security reasons, they seem to often have a standard set of behaviors, but again, for now you're going to have to look out for it. It's nice to know that at least in the future, hopefully we'll know I can use this and I can expect this will always be the same, although this other thing may be slightly different. So there are 2 pages of references. I will put the slide deck up right after this. I will link it in my LinkedIn and on the Twitter handle, so you can peruse those at your leisure. And questions?
Yeah, Freddie, we only have the one hand up, right? So ask your question and people will repeat it.
So what are you using that's like there? You're using E-Log, the nodeless evaluation that you were doing?
Sorry, using what for nodeless?
You're using E-Log.
Yep, I was asking for, the question is for the nodeless, since I was talking to, I was working, easier probably if I run around and you just.
I just noticed you had Madhuri Hachuri up there, who's, I guess, co-founder of eLotl, and they're I don't know, is all your examples for nodeless problems, were they referencing eLotl, or is it just generic?
So I asked them about Virtual Kubelet. Virtual Kubelet is, again, it's optional, but it's a basis for implementation. And then for whichever provider or platform you want to support, you do have to extend it. And it's a lot of the other cloud providers, smaller cloud. And so I'm going to insult somebody by saying this, but smaller cloud providers use Virtual Kubelet for their nodeless implementation. And I want to say, you can just go to the Virtual Kubelet link, which I do have my references off the top of my head. I think IBM does it. Alibaba, I want to say, does it. Azure is the big one that uses Virtual Kubelet for their nodeless implementation. AWS with their EKS on Fargate does not use Virtual Kubelet. I guess, I don't know what they do, but they rolled their own or something. Does that answer your question? Okay. Any other questions? And again, you can reach out to me later and I'll answer.
So if you're interested in going from like local host development to cloud, sort of what are some keywords that you can throw out for, this platform might make it easier to do that sort of migration.
So you're talking like Minikube, like you're just running it on your laptop or something like that? Yeah, I haven't actually. I've stopped testing that locally, so I don't have good answers. I know that a lot of, especially very low-level Kubernetes programmers are using Kind instead of Minikube because it gives you a lot more access to this. But again, I'm not sure how well it handles a lot of these kind of hardware platform dependent differences. Anybody else? Okay, thank you all for coming.
Thank you.
And I got time perfect.
Yeah.
I'm ready.
Speaker gifts for you, the Kubernetes operator book, and a one for a T-shirt from the CNCF store.
Cool.
Yeah, we usually have the chair for the facilitator. Were you also signed up for tomorrow? No.
Bill from Yonkers? Holy crap, right?
Yes.
Yeah.
I saw your name on the list and I was like, well, shit, I'm going to that talk.
How are you?
I'm doing well.
And I know you were at after Yahoo was that.
Deluxe.
Yes, color, yeah.
Deluxe and all. You may have met at some point.
Yeah. Where are you now?
Huh?
Where are you now?
I'm at Rubicon Project.
By the way, I just seen the East Coast. But I have not seen it.
Doing infrastructure there.
So, I mean,
Good.
one person did mention that, and I forget
How are you
which
doing? Where are you
it
at?
is.
I have Stackrock, which is up in the
We
up in
should
mountains.
probably
They do
clarify that. That's the only way you've done it, right?
Yeah, but they'll get the reporting on.
walk around.
Oh, it is.
talking about
Okay, you
Kubernetes.
shared that.
Yeah.
Okay, good.
Yeah, it is.
It's in the same source.
And I don't have to be on call,
Okay.
which is the biggest nice thing, exactly.
Yeah, and I always am pretty proactive to make sure people like hear the thing and not wait.
Yeah. Sure, go for it. Welcome. Yep. This is good at the lot zero. Yeah, you can plug that in. That should work. It's just giving a lot of just having you got so. That doesn't work, then you can switch back forward to the all right. Pretty cool for the first try. Way overcrowded. way overcrowded. Yep. Someday we will actually have a chance to do like an actual flawless tutorial. But so far, 4 years it hasn't happened. Every year cloud, and IBM Cloud decided to lock out the entire project system due to excessive connections. So.
And then do it with last minute.
Yep.
I did not leave my phone. Look, where do I put this? Probably shoved it in with everything else. Yes, I shoved it in the pocket with everything else. Fine, I'm good.
Have me tweet it out.
So you're saying pottery? Pottery?
Yes. Yep. Hey there. Welcome, everybody, to our second talk slot. You may notice if you're here that the schedule's been a little bit rearranged. And my co-chair for the containers track, Elizabeth, is going to be talking to us about one of the things that she knows really, really well, which is running Kubernetes on a mainframe. So welcome, Elizabeth.
Thank you. All right, thank you for coming, everyone. So this is a very unusual topic. I spoke at KubeCon on this in November, and they moved my talk to like another hotel because there was a power outage, because it was San Diego, and apparently it doesn't rain there. So it rained, the power went out, they moved me to another hotel, and still like 3 people came to my talk. I was super excited. It was actually a few more than that. But obviously, like mainframes, they seem like old things. Oh, I've got some blinking going on my slide. Maybe I'll just do it like, wow, that's still not awesome. Wow, that's very, it's just HDMI.
Yeah.
So, yeah.
Are you direct HDMI?
Yeah.
Plug it back in.
Ooh, that's even worse.
Are you on Google Plus?
No, I'm just events, local. Let me drop my resolution or something. What is it, 16 by 9? All right, let's see. I want to break it in a second. All right. Okay. So a little bit of background. One of the reasons I'm a track chair for the containers and virtualization track, even though I work on mainframes now, is my background. I was working on OpenStack for several years with my friend Colleen here. I was also working on Apache Mesos most recently in my last job, doing container stuff. And then towards the end of my role there, I was working on Kubernetes a little bit. And then IBM called me and said, hey, Liz, do you want to work on mainframes? I was like, what? Maybe, no. But they talked me into it. There's a lot of really interesting technology happening on mainframes these days, especially when it comes to things like containerization. And they wanted to bring me on board, even though I didn't know anything about mainframes, to talk to folks like you, like sysadmins like myself, who didn't really know about mainframes, or some of you who might, and just don't realize that there's like modernization efforts happening on the application level and things. So they brought me on board, and they're like, you're our Linux person, you're going to teach everyone on the team about Linux, and they're going to teach you about mainframes, and we're going to make everything awesome. So I am a developer advocate at IBM, and I work closely with open source projects who are looking to bring their applications to the mainframe. So as I mentioned, I was working on distributed systems, so OpenStack, Kubernetes, Mesos. And when I thought of a mainframe, I think of this picture here. Like, they're old things from the 1960s and the 1970s. No one really probably people use them, but they're not really like up-to-date modern technology. So I would talk to customers in my previous roles, and they were always trying to get rid of the mainframe. This was like the goal of this quest that they had. Like, you'd talk to customers, and they'd be like, we have this new DevOps team, and we want to make everything DevOps, and that means we have to get rid of the mainframe because it's old, and you can't use it with automation, and like all these things that are not actually true, but people sort of think that they are, because for a long time it was really hard to do a lot of automation on mainframes, and you did have to use like green type on black screens, and that still totally exists in the mainframe world, but these days if you're getting into it, you don't have to interact with that so much. So they have this team. Actually, if anyone worked on OpenStack with me, these are OpenStack people. I was like, they look like a cool DevOps team. Anyway, so they bring in like this DevOps team to modernize their application. And they'd still have a mainframe team, but they would not be part of this modernization effort. They'd be down in wherever you keep the mainframe people, and they are in the, like where they are happy. And they didn't want to be part of the modernization effort. They think maybe it's going to make them lose their job, and they're going to get rid of the mainframe. And so you'd have the new DevOps folks and the old mainframe people, who are not all old, by the way. And then inevitably, at the end of this project, whether it's 18 months, 2 years down the road, this modernization effort would conclude, and the mainframe would still be there. And you're like, what? So what would happen is they would do all the easy stuff, turn it into microservices, right? They'd take everything that is stateless, all of the web front end, and they just like parse it out and put it all into microservices. And then they get to the back end, where all the data is stored on the mainframe, and all of these really old applications are running, all of their like business critical workloads, and they wouldn't be able to move that. Like they could not replicate the reliability and everything about the mainframe. And so things would stall out there, and then they'd be like, oh, it failed. But I'm here to tell you, I don't think it failed. I think that is a fine end state, actually, because mainframes are actually really interesting machines. So let's go back to this picture, what I used to think about mainframes. So today, mainframes are still being released. IBM came out with their latest mainframe in September 2019. So they're definitely, like, the machines themselves are very modern. There's a ton of development effort happening on the hardware side. So what is it exactly? It's a big computer. Inside of like the biggest model that we have, so this is a 19-inch rack size now, and so you can have one of them or you can have 4 of them. Like it's not like you don't just like stack them. They're different configurations inside. But you can have like 4 of them all next to each other, and they just fit in like a standard spot in your data center. In a fully loaded modern mainframe these days, you're going to get 40 terabytes of RAM. And all this other stuff here. So the PCIe cards that handle things like data I/O and cryptography. And you have all these drawers that have all the cards in them. And then you also have like different logical partitions, which are essentially like what they feel like individual computers inside the mainframe. So when you put applications on them, they think they have their own computer. And then inside the logical partitions, you can add like lots and lots of Linuxes or lots of ZOSs, and I think there was a benchmark that showed you can run like millions of Docker containers on one of these all simultaneously. I don't know what the Docker container is running. It's probably just like Echo 0 or something, but like the containers are running there. One very important thing to note is that mainframes are not x86. So they are whatever you want to call them, IBM Z, Z architecture. If you're working on Kubernetes, you'd probably see S390X, because that's what the open source side of things calls them. So that's the architecture, like shorthand. But again, the fully loaded mainframe, you've got 190 processors, and they're all at like 5.2 gigahertz, which is like the fastest commercially available processor out there. And one of the really interesting things about these machines specifically is that they have really large caches on the CPU, which means they can, when they're processing data, whether it's like on the machine or streaming data, it caches a lot in the processor, so it makes things really, really fast. And that's distinctive of this processor. And I wrote a blog post about like all the cool hardware and links to like a bunch of other stuff if you're interested. It's linked there. And this is kind of what they look like inside. It took me a couple months to actually find this picture inside of IBM after I joined. I was like, what's inside a mainframe? And everyone's like, what does it matter? You're not going to like use it. You're just logging into it. And I'm like, because I like hardware and this is cool. Like I want to see one and I want to touch one. And they were like, okay, Liz, whatever. Anyway, I finally got a picture. And then one of the things one of my colleagues, petting zoo at some of the events he does, so he brings mainframe pieces and lets people hold them and touch them. And management totally did not understand this. They're like, why do you want to touch an old broken CPU? I'm like, I don't know. Don't you want to touch an old broken CPU? I'm like, my people know. And then, okay, so if you look at this, there's like lots of processing drawers and I/O drawers, PCIe things. This is like all processing stuff. There's no storage on this machine. In order to get storage, you have a separate machine. So like there's all kinds of levels with regard to latency and stuff. Oh yeah, question? How big is this one? So that's like 4 19-inch rack spots. So 19 times 4, yeah. But it fits just in the standard spot, yeah. And that's the configuration it would look like if you had 4 of them. So like in this one, like the CPU drawers are in the center. So it's not like you can pull one off and have it be its own mainframe. It's all, and they come in like size 1, 2, 3, and 4. So then we have the storage. So you can, depending on how much latency and how much storage you need and how fast you want them, you can get like little storage arrays, or you can get the big one. The big one here is like our latest, fanciest, amazing one. It's like 6 petabytes of flash storage. I don't know how much they cost. It's probably a lot. But it's really cool because it's really fast. And secretly, they run power inside of the storage machines and then just run like a RAID array inside of that. So it's all like, I mean, it's proprietary, but it uses a lot of open source technologies inside of that to handle the array. So it just never dies. So what runs on a mainframe? We got the traditional ones, ZOS, ZVM, ZVSE, and ZTPF, because IBM loves abbreviations. But what we care about today is Linux on System Z. So that brings us to where we are today. So you have this mainframe or somewhere in your organization, but you want all of the DevOps stuff. You want containers, you want Kubernetes. And you wonder, like, why did that modernization effort fail, right? So, as I've been saying sort of all along, mainframes are actually quite nice machines. They are modern. When people talk about modernization efforts, it's not actually the hardware and the underlying system that needs modernization. It's the applications and the workflows. Because now there's all kinds of tooling around your development efforts. So even on ZOS, which is proprietary, IBM's old operating system for mainframes, even the operating system itself is being modernized. There's now tons of open source tooling around all of that. You can run Jenkins on a mainframe. You can run Git on a mainframe. And so you can get a whole DevOps pipeline inside of even ZOS. But looking on the Linux side, you then have access to a lot of Linux applications. And in addition to that, just in general, like when I talk about a mainframe, like there is storage that is unmatched in the world with regard to how reliable it is. I mean, you spend a lot of money on this storage machine, but then you don't need to build a giant distributed cluster of storage and have a bunch of engineers administrate that. So instead, you just buy a box and put it in, and it never dies. And you call IBM if you have trouble. Like, we'll come and replace drives and stuff. And I'm not saying this is for everyone. Some shops may still want to go the route of distributed file systems, and that may make sense for a lot of people. But from where I was coming from, I've been doing systems administration for like, I mean, as a hobbyist, probably like 20 years, professionally for about 15. Like, it wasn't in my head that these things existed anymore. Like, I didn't quite realize that you can just buy a machine and not have to set up Ceph. So it maybe makes sense for some companies, especially if they're already invested in the mainframe. I mentioned the processors are really fast. We like to talk about 5 nines of uptime. But there was an independently verified study recently with the new release. We actually have 7 nines of downtime. Like, mainframes don't go down. They're earthquake tested. There's this fun video on YouTube where you can see one of the modern mainframes being just like shaken like crazy to see what falls out. And that's part of just the earthquake testing. There's photos online of after like Fukushima in Japan, after like the earthquake and the tsunami, like they go back in the data center and they're like, wow, what's this mess? Oh my gosh, the mainframe's running. That's weird. So these things, like, they don't go down. They have redundant everything. And so, like, when one piece fails, another one will just pick up where it left off. You also have, like, between your VMs, it's all, like, over a hardware bus, so you don't have to handle networking so much. So it's not TCP/IP. It's actually just handled underneath the machine, unless you want to do TCP/IP between your between your containers and your virtual machines. You can do that, but you don't have to. And as I said, they run Linux. And this is the thing I was so excited about when I joined, and I like totally nerded out about the history in this year. So I spent like 2 months when I first started just like learning all the history of Linux on the mainframe. And so I wrote a couple articles for opensource.com because I was like, oh, I'm going to share this with everyone. So if you're interested in more history, it's that. But Linux has run on the mainframe for over 20 years. It started with community efforts in 1998 when some folks got together. And like 1998 in Linux was like this is like when the Dead Badger essay came out, like installing Linux on a Dead Badger. You can install Linux on everything. And so these guys were essentially, and they were all guys, saying, we can install Linux on a mainframe. That would be fun. So it was like a fun weekend project, maybe a few weekends. And they were using ZVM, which is like they were using VM at the time. It wasn't ZVM at the time, but the virtualization software that came with the mainframe. But they were having fun. And then IBM's like, actually, we're already working on this. Come to some private meetings, and we'll talk to you about it. So IBM came out with their first like official patches for the Linux kernel. I think it was like a 2.2.4 kernel or something in December of 1999. So last year I had a lot of fun being like, woo, 20 years of Linux on the mainframe. So the kernel patches came out. These weren't mainlined yet. These were just like, here's a Red Hat kernel, and here's a bunch of patches you can throw at it. So they were just binary blobs that you could add onto the kernel at the time. And then in October of 2002, SUSE Enterprise Linux came out. And this is my favorite thing, because when SUSE Enterprise Linux came out, as a branding effort, they called it Enterprise Linux because it ran on the mainframe. The version for x86 of SUSE Enterprise Linux didn't come until April of 2001. So I like to say the mainframe version is the original SUSE Enterprise Linux, and x86 is the port, right? Pretty much immediately, as soon as like the IBM released patches for the mainframe, companies were picking it up. It wasn't just IBM. So SUSE's on board. Red Hat joined with their version soon after. And then in 2015, IBM came out with a Linux-only mainframe. So this machine is full. So that's the 4-rack one. It's full of processors that can only run Linux. So they've got firmware that doesn't allow them to use any of the proprietary operating systems that, or at least not ZOS. It can run ZVM, but it can only run Linux essentially. So it's like this. So we've had 3 versions of this one. So the first one in 2015, another version in 2017. And then, as I mentioned, in 2019, we came out with the latest version that this is a picture of. That's because I need water. And one of the interesting things about this one is again, like this is the first one that fits into a 19-inch rack spot, like all of them. There was one version of the Z14 that fit into the 19-inch rack spot, but in this one, they all fit. And that was a huge like thing for systems folks. They were like, I can't fit this thing in my data center. Oh yeah, this is my favorite slide. So, inside of the machine, I haven't talked at all about encryption. So, encryption is really good on these machines. And when you're running Linux on them, you're just using standard Linux tools. So on the hard drives, you're just using dmcrypt. So that's just kernel level stuff. Userland, you're using just OpenSSL and libcrypto. And there's this really great little like IBM Red Book thing that I found about security on Linux. And it was so cool to see that like for OpenSSL support, it's not some like binary blob from IBM. It's actually built into OpenSSL. Like IBM spent a lot of time working in open source projects, adding the hardware encryption support directly to the open source projects. So suddenly like you like add this little config file to OpenSSL, and then you're using all of the hardware encryption. There's built-in encryption inside of Java written in now. The most recent versions of Golang can leverage the hardware support on the mainframe. And even like the crypto library that drives all this stuff, it was developed and is fully open source from IBM. So that's pretty cool. So in this picture here, we have a Crypto Express card, and that's like an actual like PCIe card that does crypto. And then also on every single CPU, that's the green one there, obviously, that has like crypto co-processors inside of it as well. So you've got crypto on the machine, on the chip, which means you don't have to take away from your general workloads to do cryptography. And then you also have additional cards. And the Crypto Express card also serves as an HSM. If you mess with that at all, it will not let you. It'll zero out the keys if you do anything bad. So this all lives inside there and does really fast hardware encryption. And this is one of the things that keeps people on the platform. This was me getting into history nerding again with the mainframes. There's been virtualization around on these machines forever. Like virtualization was invented by the mainframe. So in 1959, you have your first time-sharing papers, which is kind of what we can talk about being virtualization. 1961 was the first proof of concept done by MIT. And in 1972, VM 370 was released, which is virtualization on the S370 mainframe. And today you can run ZVM, but also KVM. And one of the reasons KVM is so interesting is because that means you can run libvirt and the whole ecosystem around libvirt to manage your workloads on the mainframe. So you can use OpenStack to deploy things on the mainframe, and that's actually what we do in one of the machines that we run for our team. So, many companies have all these workloads already on the mainframe, and we want to modernize how the applications work, because the mainframe is already modern, as we've demonstrated. So, the first step is using Linux on the mainframe here. And this is like our vanity slide of all the cool stuff that runs on the mainframe on Linux at the moment, all the open source stuff. So this has all been handled either by the community or by the team at IBM who's done the porting effort. And the big difference between x86 and S390X from a programming standard perspective is that x86 is little endian and mainframes are big endian. And this matters because when you're compiling your software, sometimes you can run into issues in this area. So IBM works with these open source projects, or we just say like a customer wants something, so we go ahead and see if it compiles on the machine. It often does. Like we compile it for our architecture, and hey, awesome, it just works. Other times we have to do a little bit of work to handle the porting, and then all the changes are upstreamed. So all of these projects, this is not like some like special spin that we have. We actually contribute back to all of the projects for the S390 support. Some of them are happier about it than others. Some are like, what is this thing even? Why am I adding support? But other ones, like, they're all on board. And one of the ones that's been totally on board is Kubernetes. So we're here to talk about, right? So Kubernetes is on this list. It's over there under your infrastructure as a service. And the Kubernetes project actually releases binaries for S390X. And I did some changelog archaeology before this talk, and they've supported it since version, what are we up to? We're 1.17 right now. It was version 1.6 that the first S390X builds were, and that was 3 years ago. It was March of 2017. So for about 3 years, the Kubernetes project has been building binaries. There's also binaries. This is really hard to see, actually. You can just go to the download page and see. This is for the client binaries and server binaries. They also build for ARM and Power. So Kubernetes is one of those projects that builds for like all the architectures that are out there right now that are really playing in this space. So that's really cool. On the distribution side, I talked to the folks over at SUSE because I was curious about what they were working on with Kubernetes on Z. And their big thing is Cubic, right? Is that how you say it? Cubic. But it's a certified Kubernetes distribution handled by the OpenSUSE community. And for the community-maintained version of SUSE, so OpenSUSE, they are releasing the S390X builds on their rolling distribution, so OpenSUSE Tumbleweed. So if you install that on your mainframe, then you can get Cubic, and you can play around with Kubernetes on SUSE. If it was up to my executives, my whole presentation would be about OpenShift. But OpenShift just recently announced in February that there is now support for the mainframe. So this is, so IBM bought Red Hat last year, as we may know. So pretty much everything inside of IBM has turned into using OpenShift for all of our container workloads. And that includes on the mainframe. So pretty much one of the first things that was done in my team was like, we need to get on top of this OpenShift thing, and we need to get it ported to Z as quickly as possible. And that happened pretty quick, because the acquisition of Red Hat happened in like last summer, and already in February we had a port for Z for S390X of OpenShift. So OpenShift is Red Hat's Kubernetes, and so we're starting to add on a bunch of like different things to support it. So we have like application packs called Cloud Packs, where we add in like a suite of applications that run on Z and then can run on Kubernetes. But the idea is like easy delivery of containerized applications for the customers who are using OpenShift and using mainframes. On the Ubuntu side, there's the CDK, which is the canonical distribution of Kubernetes. And they were really, really happy that I was going to talk about Kubernetes. So they gave me this really cool chart, which I can show you. Like it's pretty much how you'd run Kubernetes on any mainframe. So I talked about LPARs earlier. That's the logical partition. And so in a logical partition, you run something like KVM or ZVM, and then on top of that, you can run whatever operating system you want, so the ZOS or the Ubuntu or Red Hat or whatever. So in this chart, we've got the LPAR, we've got the Ubuntu server sitting on top of that. You'd probably have like 15 Ubuntu servers running on top of the LPAR, or like 100, but a lot, not just one. But this is just simplified, obviously. So right here, we're Ubuntu server Bionic, which is the last LTS, 1804. And then on top of that, this is Canonical, so they're using LXD. Obviously, you can use Docker or whatever containerized platform you want here, but they use LXD inside of their Kubernetes. And then on top of that is where you run all of your Kubernetes workloads. So you're familiar with etcd and all of your kube API and all the other stuff that you need to run Kubernetes. And then, of course, you're running your user runtime and then all of your actual workloads on this as well. And this is how you would do it pretty much on any of the Kubernetes distributions on Z. It's always on an LPAR, and it's always got your basic operating system running. And then if we step beyond Linux distributions, there's also independent companies who are doing Kubernetes on the mainframe. The one that I work with a lot is Sign Nominee Associates. They're based out of the US, and if you go onto one of the Linux on mainframe's mailing lists, which are like old school listservs, if you ask about Kubernetes, someone from this company will definitely chime in and say, here's my OpenShift or Origin implementation documentation, and they have pretty much all of the open source stuff covered. So they're the ones you talk to if you want to do just like pure open source Kubernetes on Z. Like they're there to help you. First of all, in the community, and also for like paid support, or if you want them to do a deployment. But they're really focused on OpenShift Origin, all the open source stuff. There's also a company out of the Netherlands called ICUIT Services. And they're another solutions company, but they're focused on doing like custom Kubernetes deployments for their customers, and they're again also using a lot of open source software directly instead of using something that's coming from one of the distributions. And for both of these, their target audience is people existing in the mainframe sphere who want to do modernization. So people come to them because they're like, we want Kubernetes, and they will help them out. And usually they're customers they already had before, and they just want to add on to their services. But my point with all this, like with OpenSUSE and with Red Hat and Canonical and like individual companies coming on board with this, like there is a lot of Kubernetes support out there for the mainframe. And sort of the question is, again, like, why are all these companies jumping on board here? And why is there so much investment in here? And I mean, why does IBM have like a Linux-only mainframe at all, right? Like, for the Kubernetes side, it's really the same reason we all want to use Kubernetes. It's containerization and microservices. Like, Kubernetes makes that much easier. And it is a really good way to deliver your software. If you're breaking down the monolith, like you can still have the mainframe in the back end, but then on the front end, you can have all these stateless services and an architecture that's much more manageable. And you can have like diversification of your staff. So like some people are working on Kubernetes and some people are working on the back end. But it's simplified into smaller tasks, so you can also cross-train more easily. And then I talk about all these mainframe goodies, right? Like, for most of the people running Kubernetes, it's all about having their front end close to the back end. So they said, you know, we're going to keep this mainframe. Like, it encrypts all our data end to end. You know, it's really fast, it's really reliable. We're never going to get rid of it. But now we want to use Kubernetes, and we want that to be close to our data. And so the whole point is, like, you can integrate it with your traditional environments. You can now add all your mainframe stuff to your CI/CD pipelines. And then you've got your Kubernetes like right next to all of your data, so everything is much faster. And one of the things I haven't talked about at all is blockchain. And that was one of the most fascinating things I learned when I started working on mainframes. Like, if you were to purpose build a machine to do blockchain, it would probably look a lot like a mainframe. Because the things mainframes are good at are data processing really fast and cryptography. And that is essentially what blockchain does. So the first thing that IBM built on the Z platform, and totally didn't tell anyone, and we launched it into our cloud, it was our blockchain service. And I had no idea this ran on the mainframe. Like, they don't talk about it. Sales and marketing don't like the M word. So they were just like, it's our new blockchain platform. It's really fast and awesome. And I'm like, wait, that's running on Z. Why don't we tell people that? And they're like, well, it doesn't play well with our markets. I'm like, whatever. But blockchain runs crazy fast on these machines. So a lot of the customers that IBM is getting for this platform are a lot of people working on blockchain. So there's a few case studies out there. Things like diamond tracking, when you're trying to track like where a diamond came from. A lot of one of the organizations started using blockchain for that. So you can't change it, and it's public in some ways, so you can figure out exactly what mine the diamond came out of and make sure that it has been ethically sourced. And there's a bunch of other case studies out there. But I mean, I was like totally on board, like, oh, blockchain's a buzzword. But now I've actually learned some more about it, and there's some really interesting use cases for it. And these machines are just amazing for it. And then that all runs on Linux. So it's Linux with the open source Hyperledger, right? Open source tooling on top of that. And then one of the things that I would be in trouble if I didn't mention is hybrid cloud. So in the hybrid cloud instances, the idea is that you have some of your workloads on a mainframe and some of them just like on standard like x86 servers. So the idea here is by using something like Kubernetes is you can build all your Docker files, and then in like the architecture section you can say, okay, this one runs on x86 and it runs on S390X, and you can just define that in the Docker file. So then you build all of your images for all of the architectures, and then you put it out on your infrastructure, and then you can like move your workloads around as it makes sense. So some of them will be on the cloud and some of them will be on the mainframe. But the idea is that you like write your Docker file once, and then you can build all of your images from that one Docker file. And then you have it across architectures. And one of the reasons this is interesting of late is because sometimes there are vulnerabilities on certain processors and not on others, so you're able to move your workloads around. When you're like, if your cloud is suddenly performing not so good, you can move some of your workloads to another thing until you get that patched, or you ramp up your workloads there or whatnot. So in a hybrid cloud environment, using Kubernetes for all of this is great because it runs everywhere. So coming back to our story that I had in the beginning, where the modernization effort stopped with getting rid of the mainframe. In my role now, I've sort of gone to the story after that story. Is like, what do you do when that concludes, and how do you do this modernization effort correctly? So the tips that I have is, first, get the mainframe team out of hiding. Like, so many of the mainframe guys and people running mainframes, they are really off in their own part of the IT organization. And they are happy there. They don't want to be bothered, but you have to bother them. Like, you have to be like, hey, you folks are going to be part of this effort, whether you like it or not, and we're not going to give away your jobs, and we're not going to get rid of the mainframe. Don't have a DevOps team over here and the mainframe team over here. Like, everyone has to work together. It's like dev mainframe ops, right? Just kidding. And then again, like, mainframe is all really good at certain things, so use those strengths. Like, keep all your data there if it makes sense for your organization. Use all of the hardware crypto stuff that you can, because that's what it is really good at. And continue just using your open source tooling. It all runs on the mainframe. It's great, and it's fast, and we spend a lot of time working on it, and that's been a lot of fun. So I wanted to leave a few minutes for questions, but I also want to mention you can get a free VM on a mainframe if you go to this link. Okay, it's IBM, so they're going to ask you for like lots of personal information, so apologies for that in advance. It's like your name and your email address and what project you're going to be working on, but like it's fine. Just if you're comfortable with that, it's fine. But you can get a free VM. It lasts for 120 days, and the reason we do this is we want people to check it out and see if their applications run on it. So if you're an open source developer, or if you have an application you want to see if it will run on mainframe, you can just get one of these VMs. We're offering, I think, SUSE and Red Hat at the moment, and we're in a migration where we'll start offering Ubuntu hopefully pretty soon. But you get a VM, It's also fun to like cat proc CPU info, right, and like show your friends at parties. That's what I did. Like the first thing I did is like I looked at my CPU info and like I pasted it in IRC. I'm like, look guys, I have a VM on a mainframe. I'm super fun at parties. I don't know. But and you can also give Kubernetes a try. I actually haven't tried it, but Minikube is allegedly ported to S390X, so you can grab Minikube and try that out if you want to play around with it. I mean, the hardest part about my job is like it's just Linux. So my boss is like, write some demos of Linux on Z. I'm like, it's just Linux. So like, what am I gonna do? Like, here's how to install Jenkins. You apt-get install Jenkins, right? Like, but it is just Linux. So I mean, you're gonna get bored after a few minutes probably of playing around with this VM. But you can try to break something, and that should be fun. And see if your project runs on it. And then maybe you can add S390X support. Because the other part of my job is I give away VMs to open source projects. So if you actually are serious about building your application like Kubernetes does for S390X and giving out those binaries when you release your software, I can give you a VM that you can add to your CI/CD pipeline and use it however you want. I give you root. So you can, divide the VM up into containers or however you use your CI system to then build your software on it. And then you can have a mainframe port of your software. Unfortunately, I can't give away any mainframes. I asked for one for my garage. I'm like, I'll even take a Z13. I'm not picky. But not yet, yeah. Couldn't fit in the overhead bin. I know I wanted to bring one, but they're taller than me. No, 19 inches wide though. We do send like the shell of them sometimes out to open source events because people love taking like selfies with the Linux One machines. Like I like taking selfies with the Linux One machine. I don't have Kubernetes. I don't have any mainframes, but I do have stickers and socks. Actually, if you're really interested, I'll give you a pair of socks. Anyway, so that is all I had for you. So I'm going to open it to questions for, I've actually got like 9 minutes. So if anyone has questions, I will repeat them. And I'm around all weekend. So. Right. So the question tends to be around like workload optimization. When you take like a rack of x86 machines, move it over to a mainframe, like what is the number there? Like how much performance am I expecting to get, and what is like how many virtual machines am I going to be able to bring over? So I have like the typical IBM answer for this, and it depends. Unfortunately, like it actually does. Like that is the real technical answer as well, because it depends on what your workloads are doing. If you're doing something that has a lot of like data I/O or crypto stuff, you're gonna be able to like shrink down like a dozen racks into one 19-inch mainframe, for instance. And then it's really just a lot of trial and error and working with like your IBM support staff, whatever, who comes with the mainframe, to decide like what your workloads should be and like how much resources you're gonna spend on each thing. If you're doing a lot of like front-end stuff, like serving up web applications and stuff, like we don't really recommend you run a mainframe if you're running a website. That's not really the right workload because you're doing a lot of networking. You're not doing a lot of data-intensive stuff probably. And so it really depends on what your workload is. So we could reduce like, a whole bunch of x86 servers down, but it really depends on what you're running. And it's like orders of magnitude depending on what you're running, because yeah, follow up. Right, so the question is around modeling. So sort of, there is a tool out there that talks about like energy savings, so you can sort of estimate like how many x86 servers and the mainframe and then how much energy savings you're going to have, which is actually quite significant, but you sort of have to know how you're already going to be dispersing your workloads and how much resources you need. So it's a kind of a hard question to answer, unfortunately. No, there's not really like a benchmark that tells you like this is that, yeah. And I'm not sure how much that is actually a technical limitation and how much of that is, you know, IBM being IBM. Unfortunately, so I think part of it really is a technical limitation. Like they don't want to put numbers out there that people can't meet because their workloads are so vastly different. But yeah, it's good. That's a good question though. Yeah, one in the back. Actually, could you step forward a little bit? Thank you. So the question was around machine learning, power, and mainframes. So the first thing is that mainframe and power are two different things. Okay, good. So there's actually a bunch of stuff out there about machine learning. So the first thing I'll say is like, since it does data processing really well, I mean it is a good platform for AI and machine learning. But we also, for a lot of our customers, we tend to partner with Watson. Because the Watson team has done, like the IBM Watson stuff has like actually has data scientists, and they are very focused on running like the most, I guess, how do we say, like, the work that they do makes more sense than like building it yourself on a mainframe. So it's really around like the Watson literature you want to look at, and then how that can be hooked in with the mainframe, which we do have documentation about, because it may use the mainframe as a back end, and then it's using, I think does Watson use Power? I'm not even sure. But that's really where like most of my knowledge about like the AI and machine learning stuff comes from, just because that's where we're positioned on it. Yeah. I'm not supposed to talk about it. Okay. All right. If there are no more, one more. So the question is, there's a port of some Python modules, you said? Python in general. So yeah, so IBM is maintaining ports of a bunch of Python stuff. Is there plans to upstream that? So I don't know specifically about Python, but I do know that our team works really hard to, I mean, like our team is very embedded in the open source communities, and usually when we have to fork something bad went wrong, because we really, like we submit all our patches to the projects, and they're really, like these people understand open source for real. And so if there is like a reason, it could be like some Python project said we're not going to accept that because we don't want to maintain it forever, and we'll be like, well, we'll maintain it, and they're like, yeah, we don't trust you, so we're not going to accept the change. And that's the biggest problem we run into, is people just don't see the value of the mainframe. So like, we never even heard of this architecture. Why would we want to add the support for our project? So I would say like I don't know specifically, but I'm sure there has been efforts we made to make it upstream, but I don't know what is going on there. We do try. Yeah. Yeah, so the question is, with bringing the mainframe developers into like the DevOps modernization efforts, how do we do that? It's honestly really hard. The general interface for the mainframe is that people tend to use is ISPF. And the people who've used ISPF, it's green on black greens, like they're super fast with it. Like they think they can get so much done by using ISPF that they don't want to move to more modern IDEs or interactions with the machine. They don't want to use Jenkins for their pipelines. They don't want to use it. They want to use ISPF. So the one thing that has been actually really effective is showing them that they're not actually faster by using ISPF. So we have actually sat down and there's one team that has sat down and put a bunch of ISPF, here's all the tasks that you should do in ISPF, and given that to a hardcore mainframer, and then has brought in the DevOps tooling and said, okay, now do the same thing with this with all of the new tooling we gave you, and they give them a day to finish it, and then they benchmark the two, how fast did you actually do it, and when they show them that the new DevOps tooling that they brought in is actually faster, that's when they start believing you. But it's hard because they want to use the old tools. And I mean, learning new things is learning new things, right? So it's really about showing them data and saying this is going to be faster, this is going to be better, and being very clear about why it's faster and better. Yeah. And also, we're not going to get rid of your job, but the whole software industry and showing them in general, this is the direction that things are going, tends to be somewhat compelling as well. And plus, when you learn, how to use pipelines, you can go and get a different job, and you can change your career and move on from that. So also showing that the whole industry has gone in this direction can sometimes be useful. Yeah, but I think it's probably the biggest challenge in our org is getting the legacy mainframers using the newer tooling. And I think we're out of time. It's lunchtime.
No, it's not.
It's not? Oh.
Yep. Coming up next, in 15 minutes, we will have serverless.
Here.
So building your own serverless platform. So coming up in 15 minutes, we'll have building your own serverless platform at noon. And then after that is the lunch break. So thanks, everybody. Take your seats for serverless in 15 minutes. Thanks.
Thank you.
Yeah, I should have brought hand lotion with me.
They're in my backpack down here.
Test, test, 1, 2. Testing, 1, 2. Mic check, 1, 2. Test, 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 1, 2. Where were you getting hissing and popping from?
Getting it earlier, so say something now.
Test, 1, 2. Mic check, 1, 2. Testing, 1, 2. Test, 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 1, 2, 1, 2. Mic check. Testing, 1, 2.
Here's our next speaker. Let's go ahead and try Here we go. Okay, you want to check the mic? We've been having trouble with this, so we've got the audio tank.
Hello? Hello?
So put it on.
Oh, okay.
Otherwise, you're going to get feedback issues.
Hello? 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 Okay. Hello? Are you able to hear me? No? Okay. Hello? Will you turn it off? How do you turn it off? Oh, there was enough. It's good, no?
Yeah, we just got to keep testing it until we get it free. You can see it's working, but it's just...
Yeah. Hello?
Yeah, that was the problem that we had with the first Let's Allow. Where it picks up too much, you know, you're
Hello? Is better? No?
Talk a little bit, just say... Testing, mic check, 1, 2.
No, mic check. Mic check. Hello? What? Yeah. Huh? Hello? Okay. Sorry, a little bit far away. Hello? Hello, mic check. Is better? Yeah, it's catching me. Yes.
So every time you move, it's going to...
Yeah. Hello? How is it? Yeah, okay. Hello, mic check. 1, 2, 3. Okay, it's good? Okay. Yeah, but is it going to like, when I talk, it's going to make some noise?
Just from your breathing and from when it touches your face. So when it rubs against the microphone, that's what causes it.
Okay.
That's scratching pop noise.
Okay.
So if you hear that too much,
Just take it out, yeah.
Or it's too close, yeah.
Okay. So now do you hear some noise?
Sorry, these are the volumes it's going to stay at. So
Okay.
if you're not hearing yourself, it's not working.
Okay. So now do you hear some noise? No, right? When I'm not talking. That's fine.
You should be good.
Okay. Okay.
The difference between too far away and too close is about half a centimeter.
Yeah, just based on what you want. Is that what always you agreed?
Yeah.
And then it dropped it place.
Yeah, for speakers, soft voices, there just was no point. The mic was not done to hear her, but not to be popping and making noise.
PowerPoint. Hi, I'm from AV. So
Okay.
I wanted to take a quick look at what's going on with these slides because it seems like you're having a bit of an issue.
Right.
Is that correct? So that's well seated. That's well seated. Are you in mirrored mode or something else?
Just in presenter mode.
Can I take a look at your display
Yeah,
settings
sure.
real quick?
Sure, go ahead.
So let's jump up here and say set preferences. I'm Michael, by the way.
Okay.
From the AV team. We saw a few. What is it doing now? All right.
No, it's okay.
That's fine. But I never saw the display settings come up. Did they pop up over there?
Oh, I think it did. Probably.
Projector is trying to find your input and finding me. Fun. Okay. I'm going to drop this out. What time does your talk begin? Okay.
2 minutes.
Yeah, so. System preferences, come on. What is going on here?
Maybe let's disconnect it and then switch, change the display settings.
That looks fine, that looks
Because
fine.
at least then it will show up on the screen.
So if we do that.
Oh, no, actually, disconnect
Oh, I apologize. All right, displays, that looks fine, and you've got it set best for the display. Now we plug the display back in. And is it going to come up happy? It's going to kick the display settings over there, which I can't see because it's flashing. So, is there an issue on the projector side here?
You see, it's an issue with it detecting the actual resolution of the projector, and so it's trying to push a resolution that's too high.
And is there a way I can pull the...
He's using a dongle, yeah?
He's got a dongle here. Have you tried our adapter?
Okay. Yeah, I say try swapping dongles, because that's worked for me.
Yeah, because Mac dongles like to. This one? This guy right here. So go ahead and try that. And let's put this in here. Trying to get it so that where, do you know, is your display over here? Can you tell me?
But it's not giving you options to change the resolution. So you really need to do it.
There we are. So arrangement, that's fine. I need to look at that. Did I not grab the right window? There we go. I need this guy, and I need to pull this over, and I need to say scaled. And 1080p or 1080i, I think they want that one. There we go. Well,
hold on.
perfect. Stable,
Okay.
happy. That's what you needed, was to get that 1080i. Fortunately, it was kicking the window over there. Now the question is, what is Office going to do to us when Office kicks in? So go ahead and run presentation mode from Office. And you've got it on the external display.
There we go. Yay, thank you.
It's just that one setting that was lost over here. Well, you guys are set up, and hopefully you're behind schedule.
Yep. Oh, did that come off your ear?
Sounds like it's not turned on.
Yeah. Turn it back on.
Hello?
Cool. Okay, thank you for your patience, everyone. Our next speaker is going to explain to us how to build your own serverless platform.
Yeah.
So if you want to know about serverless, you're in the right place. So take it away.
Thank you. Thanks, Josh. Hello, everyone. Thanks for coming in. And I am Murugappan Chetty. I work as a principal engineer at Optum. And I work on serverless, service mesh, and observability there. I'm also a small-time open source contributor. So about my company, Optum. Optum is part of United Health Group. Just like how United Healthcare provides health benefits, Optum provides health services for United Health Group, I should say. And Optum also works with a wide variety of customers across the healthcare domain, and you can see some numbers here. So that's about my company. And today I'm going to be talking about how we set up a serverless platform in my company and how we are currently managing it, what are all the use cases that we are running. And if the time permits, I'll also show a small demo. So how did we get started? Back in 2016, we had to develop some Alexa skills. So these are some live skills that we have developed. And for which we had to use AWS Lambda. That was our first exposure to serverless, and we really liked the experience. It was really simple and powerful. So, and we thought how it would be to bring it to an on-premise platform and show it to our enterprise customers. So if we had to do that, the things that were on our side was majority of our workload is on-premise. And the container system, container ecosystem was kind of mature at that time. We were already on Kubernetes and OpenShift. And we had like a lot of compelling use cases within our company which could come on the platform. And we were also aware that it would be always compared with a public offering like AWS Lambda or Google Cloud. And we had to do the cost effectiveness compared to a vanilla Kubernetes or OpenShift. So that being said, around 2018, early 2018, that's when we started. And we compared about like 6 open source platforms. I'm not going to mention those. If anybody wants to know about what are the platforms were, we could have a discussion after this session. And based on that, one common factor between all of them was everything was container based. So the functions or the service would run as a container and scale up and down. So based on that, we set some principles for ourselves. So most important thing, it should be request based compute, and scale to 0 is the main one. And we are already having a solid Kubernetes-based platform. So our platform, we wanted to run it on top of Kubernetes. And it should obviously support all the programming languages, even PowerShell or shell script. And observability, we wanted it to be a first-class citizen. And this ecosystem was really evolving. Now also the serverless ecosystem is rapidly evolving. So living and learning was always part of the culture. The two actors that would be involved in this is an operator. Operator is the one who's going to be building this platform and hiding all the complexity, and the users are the one that's going to just develop some functions or services and be just concentrating on the business use case. So keeping these principles and actors in mind, we put together some capabilities that we wanted to form a serverless platform. So, or I would call as a part of the puzzle that would make the serverless platform. So first one, and this one is the core of the platform, is the build, event, and serve. That is the three pillars of any serverless platform. So building is the way that we give to our developers to build their functions and functions or services, and serving is the function management lifecycle. So scaling up, scaling down, and for eventing, how once the service is deployed, what are all the ways that service could be reached. And for all these things, we used an open source platform called Knative. Anybody here aware of Knative or already using it? Yes. Okay. So I'll talk about Knative in the next few slides. And for multi-tenancy, for any managed serverless platform, the most important thing is multi-tenancy. Fortunately, Knative and Kubernetes both are multi-tenant by nature. So with Kubernetes RBAC and integration with the token provider, you can clearly segregate the roles and have multi-tenancy. Security is, in a microservice world, security is usually developers' concern. Developers usually take care of the security for their own application, but we wanted to give this as part of the platform itself. So for which we leveraged Istio's RBAC and Istio's TLS capabilities. And we want to have observability and resiliency as first-class citizens, which I'll go over in later slides. So then eighth one is the one that we developed in-house, and we wanted to give that extra level of convenience for the users so that they feel at home with this platform. So that we call it actually as a serverless dashboard. And these are a set of APIs which I'll go over, like what are all the set of APIs and what abstraction it provides. And along with it, comprehensive set of documentation and CLI called KNCLI, which is also part of the Knative project. So these are how the platform stacks up. I think it's really small, but what all the components involved are like Kubernetes, Istio, Knative, and on top of that, we have that serverless dashboard API that we have, and we use Keycloak for the token provider, and our observability stack consists of Prometheus, EFK stack, and Jaeger for tracing, and so that's it. So, okay. Now I'll go into the components. So what are all the components involved, and I'll just go and see like how we are using it. Yeah, Kubernetes is our base, and we all love Kubernetes. I'm sure most of you are already like know what Kubernetes does. But here I'm just going to talk about to write a service in Kubernetes, what does it take now? So we have to write two manifests. One is a deployment, and another one is a service. And what it lacks currently today is like there is no per request load balancing. Auto scaling is just based on HPA, and there is no concurrency control, meaning that there could be like thousands of requests concurrently coming and hitting in the same pod at the time. So this is where Knative comes in actually. Okay. So here, Knative is a popular open source project actually, and it has like more than 400 contributors from 60 plus companies, and mainly it's a collaboration between Google, VMware, IBM, Red Hat, and SAP. The community is really good actually, and everybody is welcome there, and the Slack channel is very active. And even the Knative serving lead once posted that asking dumb question is a superpower, and we have unleashed it many times there. And Knative comes with like three main, it used to come with three components actually: serving, eventing, and build. Build is now discontinued for Tecton pipelines. So serving and eventing are the main two components that we are concentrating on. Serving is kind of really mature, and it is multi-tenant by nature. So main feature of Knative serving is a control plane. Its job is to scale the pods up and down in a tenant namespace. So whenever user gives a manifest to create a service,
Knative deploys in the user's namespace, and then whenever the request comes in, the pod goes up or down. It's all controlled by the Knative control plane. And obviously, there's a queue proxy, which is a sidecar which sits along with the user's container, which gives all the information related to the container, when to scale up or down. All those information is fed by the queue proxy. And related to auto-scaling, there are two auto-scaler controllers that they provide. One is request-based, and another one is CPU-based. So you can choose either one of them to auto-scale your services. And for networking, they use a gateway, external gateway. It could be either Istio or Glue, and they also support a gateway called Contour or Courier. Currently, only Activator is part of the your request path. So once you have deployed the service in the Kubernetes namespace, and only during the cold start, the Activator comes in your request path. So once the pod is up, the calls directly go from the Istio ingress gateway to your application. Knative control plane is not anymore in the request path. Okay. Any controller that comes inside Kubernetes, we know there are going to be some CRDs. Knative also comes with its own share of CRDs, but the CRDs that we need to be aware of is mainly the service. The service comprises of encapsulate three other CRDs within. One is revision, second one is configuration and route. Revision is an immutable object. So when you create a service, when you create a Knative service similar to a Kubernetes service, a revision is created, and that means that is immutable. And anytime when you update your container, a new revision will be created. So if you want to go back to the older version, you can go back to that revision. Also, you can do A/B testing between these two revisions, or any kind of canary deployments between these two. Also, the traffic, you can adjust the traffic between these two revisions, like if you want to go 50-50, 70-30, like that. And the route is the CRD that's going to have the traffic-related information. Configuration is a single object, and it's going to have the current state of the Knative service configuration. So that's about Knative. And Knative uses, as I told earlier, Knative uses Istio for its networking purposes. It creates services in this format, like service name dot namespace name dot the domain name. So we configure our DNS in such a way that any request to start.domain name should be routed to the Istio ingress gateway. So the Knative expects Istio ingress gateway or the cluster local gateway to route the traffic based on the host header information to the correct service. So, and that is one thing. And the additional features that we are expecting out of Istio is TLS. So the TLS handshake is managed by the Istio ingress gateway. So we load the wildcard certificate as a secret, and Istio ingress gateway has a component called secret discovery service, which discovers the certificate from the secret and handles the TLS handshake for you. Currently, Knative is developing something called Auto TLS. It's kind of in alpha. What Auto TLS does is, whenever you deploy a new service, it's going to generate the certificate automatically for you with the help of Cert Manager. So the way it works currently now is the certificates are wildcard certificates. With Auto TLS, you will get the certificate per service. So while showing the demo, I'll show you how it looks. And the other two security aspects that we look for Istio is authorization and authentication. Istio can check a JWT token for who is the issuer, and it can also check for the claims, and based on that, you can protect your services. So the maintainers of Knative, when they developed and released it, how they are positioning it is as a low-level set of primitive APIs. On top of that, they could build some high-level user-friendly APIs. So that's what Google Cloud Run is doing on top of Knative, or a Project Kaima from SAP is doing, and Red Hat is also bringing something in the OpenShift. And so for our customers internally, we built a set of APIs, and we call it serverless platform APIs. And it mainly concentrated on 4 areas. It's highly opinionated for the company. And first one is tenant space management, where the users can come in and create their namespace, add users, set the kube context. Second one is like, this is the most important thing where the users can create services, do canaries, add authorization. And the last one is function tester. So where the user has to, if this component was not there, the user has to know about Kubernetes, Istio, and Knative, and know about all the CRDs, all those things. We are just abstracting it and making it a little bit easier for them to get started with this platform. And with this set of APIs, the user doesn't need any kubectl or Kubernetes dashboard. And this API also enforces good standards, like you always need to specify your CPU in memory. That is the problem with any Kubernetes operator. You ask people always oversubscribe and ask for more CPU in memory. So this is kind of a standard that we enforce. And all the functions or services are run as non-root. And we also enforce versioning. So in Knative, when it does resource versioning, either you can give your own resource version name or you can ask Knative to generate one. So we enforce to give the resource version name. So when it comes for backup, it's really helpful. And these APIs are also goes well with our inside Jenkins libraries that we have. So the next one is we spent a lot of time on getting metrics and logs, right? Because when we say people don't have to access kubectl or Kubernetes dashboard, the metrics needs to be really well organized. So my friends here who have come along with me, Wei and Somadeep, they are also they were instrumental in building this metrics setup actually. So the problem here is like Kubernetes comes with doesn't come with any metrics setup, but we can set up Prometheus for Kubernetes to scrape the metrics. Istio comes with its own set of observability components. Knative comes with its own set of observability components. We have to consolidate all those into one. So that's what we have done here. For Istio, we can define a service monitor and then get the metrics into the Prometheus operator. For Kubernetes, same, we define some service monitors to get it in the Prometheus operator. And for Knative control plane and the user metrics, we define some custom scrape configs to get it in the Prometheus. And for long-term storage, we use Thanos, backed up by object storage. And we spent a lot of time with Grafana dashboards to make it really simple for the users and for the operators to know what, to get to know what's going on within the cluster. The next thing is Knative comes with this EFK stack as it is. They give you the template to just deploy it in your Kubernetes cluster. You can just take their Fluentd configuration and use it, but the way Elasticsearch and Kibana works, we need to play around with something. It doesn't work out of the box. So we did some work on that, and now all the logs, only the user container logs. And you know, if I try to scrape every single Kubernetes logs, it's going to be like too much. So we are just scraping the user container logs and into Elasticsearch, and we visualize it using Kibana. Okay, so once the platform is all set up, the next thing we need to see is like how are you going to manage this platform, for which I'm going to just touch about 3 areas which we mainly concentrated to check on the platform. First one is like planning for the capacity. So once you have your platform up and running, you need to know when you want to upgrade the resources, when you want to add more nodes. So we have a single place of in the Grafana dashboard where we could see exactly like how much resource is being utilized and when we need to upgrade. So always during increasing more resources, we had to back it with correct facts. So this is the Grafana dashboard that we have. Second one is to monitor our cluster, for which we have like 2 ways. One is a Grafana dashboard and Prometheus alerts, which we have customized for our cluster. And we have also developed a probe tool, which is very extendable, which probes at different points of the cluster and currently says what is the status of the cluster. And slowly, if we see repeated issue, we also add automation to it. For example, for certain issues, it is worth restarting the node. We identify those kind of issues, and automatically node gets restarted without letting the user know. Of course, it sends an email to us, but those things are automatically handled for us. Like this, like if there is an issue happening again and again, we just filter it out and then take corrective actions automatically. And third one is like for the user. We have developed a simple dashboard which tells like how many functions they have or services and how many times they have run it and what is the CPU and memory utilization for their functions. Okay. It's about any platform without user is not much useful to the company. So we spend a lot of time make the users feel at home. So we develop like comprehensive guides for them to get started with. We mainly concentrate on two areas. First one is like building and deploying, how we can help them. Second one is how to observe their functions. For building and deploying, the main thing is, as I told you earlier, containers. The Knative platform expects a Docker image to run it as a function. So people are already familiar with Docker, it's easy. They can just get started and they can work on it. But we wanted to get people who are not familiar with Docker, but still we wanted to pull them in. So for that, there are like multiple tools currently available. I'll just touch on something, okay? For the Google Container Platform has two tools. One is called Co. Second one is called Jib, okay? So Co is for building container images for Golang, and Jib is a Maven plugin or a Gradle plugin for Java. And Fabricate is also a famous plugin from Red Hat, which is also really good. And these are three plugins we mostly use, along with another CLI called OpenFast CLI. OpenFast is also open source serverless platform. Their CLI is really good because we could just, it comes with a set of templates for a wide variety of languages, even shell script or a PowerShell. So infrastructure people who would want to just put some functions here and don't have much knowledge on Docker, they use the OpenFast CLI to develop their Docker images and deploy it here. We are also checking on Tekton pipelines and build packs, which is like growing right now. And when it comes to deployment, we have like two opportunities. One is the serverless platform APIs that I told earlier. So these are a set of APIs that we offer. And so here it just asks for very less number of variables to get started with. You just need to give the name of the service and the image name and which port it runs, and you're going to get an URL for you to get started. And there is also a KN-CLI which comes with Knative. This CLI is like really powerful. You can get the same, but instead of kubectl, you're replacing with KN-CLI. That's it. You can get started quickly. So this is the dashboard that we built for the user. So here in the front, you can see the number of times the function run, and then how much CPU and memory it's using. And you can see here clearly that the CPU spikes and goes down every interval. So this is a periodic function, and then every time it's not used, the CPU and memory usage goes down. Okay. Next, I'll just go over some use cases, early adopters for the platform. First one is the infrastructure automation use case. For this one, it's based on a pattern called three-factor pattern, coined by people at Hasura. Hasura is a GraphQL engine. So that's the GraphQL engine we're using, and it's a GraphQL engine on top of Postgres. So three factors that they are mentioning here are GraphQL, eventing, and serverless. So when a user creates a request for infrastructure automation. So this is mainly concentrating on decommissioning a server. So whenever they want to decommissioning a server, they use this. So when a user comes here and he says that he wants to decommission his server, there is a request to the GraphQL engine, and it persists that in the Postgres database. So based on that, an event is triggered, and all these functions are called. And these functions do some action, and then they persist again to the GraphQL engine. So right now, the user is still waiting on the subscription. So when there is a change happening, it is reflected on the UI. So this is the first use case, and it's currently running in production successfully. Previously, it used to be a manual effort, and we automated this one. This is a common use case around most of the organization, file processing. And file processing usually is done with the ESB solution. And we were also doing this with a commercial ESB solution, which we re-architected using this platform. And we used to share the store in Kafka. And currently, we are like trying to re-architect using this Knative eventing. I didn't go over Knative eventing. In the end, I'll just touch upon like what Knative eventing is. So this is another infrastructure use case, or like this is a common pattern across my company, whoever has Prometheus. So based on a Prometheus alert, functions are triggered. So whenever there's a Prometheus alert for some action, each alert is mapped to a function, and that function takes the action. So when there's an alert, it goes to a message queue, and the message queue triggers the function. So this is another use case that we are trying to re-architect, is the Knative eventing. Serverless is kind of synonymous with IoT, because IoT is also event-based. And in the data ingestion pipelines of the health devices, we are using Knative here. So finally, this is a machine learning use case. So we have like a couple of machine learning use cases. What it does is, like, there's a machine learning model this service uses to process the data that has been sent inside. And you can see here, like, we did some benchmarking with it. You can see here, if it was supposed to run on just a container platform without serverless, it would be always consuming this 5 GB and around like 2 or 3 CPUs. It's a constant one. And this use case, they didn't have like request constantly 24/7. So when they used to get it, they used to get it in loads. So that's why they changed it into a serverless platform. And when we did it for like a 5-minute time, the pre-serverless one used to process about like 50 transactions. In the serverless, we were able to process around like 400 transactions. Other prominent use cases are mainly the infrastructure. People kind of love it actually, because who are maintaining these large machines, they have these small jobs running here and there. There's no centralized place to put it. Now all these services and functions are running inside this platform. It's a centralized place for them to manage. And we have a lot of ETL jobs as well. There is a couple of voicemail processing services running. Serving MN models is the other one that we are looking into, but with KF serving become generally available, we'll be looking into that. Okay, so these are challenges related to the serverless platform itself. Like, it's not just related to the platform that we have, it's common to any serverless platform. DB connections to database like MySQL or something like that. Every time the service comes up, it will establish a new connection. If you are using any NoSQL or a Cassandra or something like that, it's fine. No, we are not having any problems. We are mostly use SQL database. But if you use a traditional database, sometimes we have this connection pooling. There's no connection pooling. That's a problem. So how we mitigated this is like we used to have a stateful microservice which will handle all the database connections for those functions. Second one is like a culture problem. The default resource allocation, people always ask for like more resources, and this is like with more metrics, and we were able to help the users say that you are asking like 2 GB or 3 GB, but hardly using like 100 MB or 200 MB. So it's more like a culture thing. Cold starts are always going to be a question for any serverless platform. The best way is to mitigate them, and Knative is also taking a lot of efforts to mitigate this cold starts. For long-running functions in this platform, I mean, you can run functions like worth like 3 hours or 4 hours, but we really need to make sure that it's stateless. So if you're going to store the state somewhere and then keep on running, that's not worth it. You just need to change it to a microservice or something like that. But if it's not storing any state, just processing and keeping on running for 1 hour, we currently allow them to do it. Java functions was another problem. The reason is like mostly all the microservices that were earlier built were using Spring Boot. Spring Boot is really good for microservices, but it really takes time for starting up, and by default itself it takes some memory. So how we overcame this was like using a framework called Quarkus. Quarkus is really a great framework. It is based on GraalVM and Hotspot. It starts in about like milliseconds. You can build binary images for Java, and you can compare the memory usage for Spring Boot application connecting to a Cassandra database. It takes about like 270 MB, but here it takes hardly like 20 MB, and it starts in about like 0.4 seconds. So whereas the Spring Boot application would start in 20 seconds. Okay, and before I go to the demo, these are some of the points that I want to stress. Timeout with Knative is configurable. You can configure as much you want, but there is you need to fix on some time, and you should say because it's not ideal for storing state, and you should enforce that the applications are stateless. And there is no way to mount a PVC also. Knative makes sure that you cannot mount a PVC. The only volume that you can mount are configuration maps and secrets. So there's nowhere you can store state within the application. And while upgrading the Knative or Istio to a newer version, what we found out was sometime when we deleted the CRD by mistake, it deletes the resources also. So it's a good idea to back up your resources. And we also developed a small tool to back up the Knative resources just before upgrading the Knative services. And finally, about eventing. With all the open source serverless platforms that are available today, it is either it's only invoked by webhook. Okay, so in the webhook, the problem is like consumer doesn't have a say. Only the producer keeps on hitting the service with the webhooks, and the consumer doesn't have a say. That's where the cloud events come into play, which gives a proper way to define your events. And with Knative eventing, it gives a proper framework for that. And the producers can produce without even the consumer coming and consuming it. So that kind of framework is given by eventing, and any consumer can go to the any producer and get that event from it. The another project that we are closely looking into is Kubeflow, which I don't have a lot of information right now to tell. Okay. So I just want to show a small demo. This is not about the platform, just about why should I? How should I bring it in? I got out, man. Which side? Maybe that. There's only one, right? Oh, okay. How should I make it big? Oh, I cannot see it from here. Okay, so I have Knative and Istio installed in this Google container platform. And what I'm going to do here is deploy a sample service which is going to get the Twitter trends from Twitter API. It has two services. First, one service is going to return the where on earth ID, and the second service, which is the main service, going to return the Twitter trends for us. And oh my God. It's really hard to do it from here. Okay, so I'm going to use the core CLI here. So this is my K8 YAML actually. Okay, let me apply that. So all I do is co-apply. How you used to do the kubectl apply K8.yaml, you can do co-apply K8.yaml, which is going to just build the image and then as well as deploy the Kubernetes for us. Oh, Docker is spelled wrong? No, I'm just putting co here. Okay. Okay, so it's building the image. So it takes the base image as the Dristroller's image that Google gives, and that's it. It's building the image, pushed it, and as well as like run the image for me. So these are the two services that you can see in the bottom. So one, you can see automatically there's HTTPS, so the certificate is there, and that is the service that I'm going to call. And second one is the internal service, which is not accessible to the outside world. So it has the end as .service.cluster.local. So that's why it doesn't have a certificate. How can I? Wow. I want to go to the top, but I'm not able to go to the top. Come here. I want to minimize this, man. Minimize. Oh, there you go. Hey, what's wrong with you? To enter it.
Sorry, demo bots. Yeah.
How does it go? I moved there. At least put it in this thing, browser thing. Okay, go to the next one. Go to the next one. Oh, okay. Okay, this is calling the function, I think. Yeah, this is calling the function to, it's starting up, so that's why it's spinning. And it'll print you the Twitter trends for you. So at the same time, you can also embed, so this is the Twitter trends for you. And at the same time, you can also embed multiple endpoints. So any other serverless platform that you see, right? So they'll be just in a single endpoint. So now you can have like multiple endpoints in the same service. So one that gives you the Twitter trends, one there is you can also embed a Swagger, or you can also have multiple endpoints for you. And this demo is actually in this GitHub page. So what I told earlier was like, if you see this K8YAML, this is my deployment artifact. Oh. And you can see the image names are just the direct GitHub source paths, not the Docker repo. And so code just needs Go source path. So whatever is in the source path, it's going to compile and then create an image for you. Okay, that's it I have. Any questions?
So, questions?
So your service scaler, Kubernetes already has the ability to do service scaling, dynamic service scaling. Is there a reason you didn't use the Kubernetes service scaling, or?
The HPA, Kubernetes HPA?
Yes.
So the Kubernetes HPA is kind of slow. So we use the Kubernetes autoscaler for the platform components, but Knative itself comes with a set of autoscalers which are like more fast than the Kubernetes scaling. Yeah. Okay, so it's based on your use.
You want to repeat the question?
Yeah. So how do you mitigate cold starts is the question. So it's based on your use case. Suppose if it is going to serve a web endpoint, a web, then it is always good to have one pod up actually, whichever is your main pod that needs to be up, and then scaling can be handled. And otherwise, whichever is the calling application always needs to have some kind of retry mechanism, retry with pushback. Sometimes it doesn't start within 60 seconds. If it's going to be a huge machine learning image and takes a lot of time to pull and start, then it's better to have some kind of retrace. So these are the two things that we used actually. Otherwise, for other ETL jobs, you don't worry about like cold starts. So it's going to be run in the night, and you don't mind about it. Thank you. No problem.
You mentioned a bit about Prometheus scraping. So how does Prometheus, what kind of scraping Prometheus does for the serverless function that people roll? Like what kind of key metric do you guys monitor on? Because it's like a short-term kind of thing. It's not like a long-term running process. So how does that work?
So first thing is like it is always up for like 30 seconds. And our scraping is for like every 3 seconds. Just for the user containers, we scrape for 3 seconds. And this scraping is user, if he wants, he can add a Prometheus endpoint also. But we are scraping from the sidecar container metrics called the Q-proxy. It just has the information about like how many times the request came and how much CPU memory it has, like very limited memory. That is provided by the platform itself. Okay.
And how does the development experience look like? So if I'm a serverless developer, right, and I want to develop against the Knative stuff, do I have to install all of the moving parts like Istio, the Knative operators, Kubernetes, or you guys spin up like a development like environment so then developer can work against it? So how does that work? How do I test? How do I run?
Okay. So there has to be an operator managing the platform for you. So the developer, for Knative to run, it needs Istio and it needs Kubernetes, it needs all this setup. But it is a managed platform that a single team can manage, and you as a user can leverage that. So that's what we are doing in our company. So there's a small team of like 5 people managing this platform, and this whole company is like taking use of it. Correct. So all the developers are going to just call this, yeah. So that's where we have this namespace segregation in Kubernetes, right? So in Kubernetes namespace, we add role bindings, which are mapped to each role binding has a user information, which is mapped to the token that they provide when they log in. Okay.
Oh, okay, hold on.
Did you use all the supported products, or did you do everything yourself? Istio and Keycloak integration, for instance.
Yeah, we just did it, we took the open source version and we did it on our own. Yeah. Yes, on our own. Yeah. But there are good documentation available for Istio and Knative.
And it includes Keycloak as well.
Yes, Keycloak we had a setup. Yeah, Keycloak is we've been using Keycloak for more than 2 years, and initially it was tough. Now we have kind of like okay. Yeah.
Okay, well, thank you. Thank you very much.
Thank you.
And we're going to break for an hour for lunch, and then we're going to come back. Samuel Karp, one of the Containerd maintainers, is going to show you how to hack Containerd. So please come back for that.
Test. It seems to be working. Test.
Oh.
Seems to be. Is that working? Can everyone hear me?
Hey, folks. Okay.
Cool.
Well, hello everyone. I hope you had a good lunch. So I'm pleased to introduce Samuel Karp here, who's going to be talking to us about extending Containerd. Thank you.
Hi, everyone. Just if at any time you can't hear me because I'm not holding the mic close enough, please raise your hand, let me know. We don't have the clip-on mic working very well today, so I'm going to start with this. As Emily introduced me, I'm here to talk about extending Containerd. And just a little bit about me, I'm an engineer at Amazon Web Services. I've been working in the container space for about the past 5.5 years. And I would just want to give you a brief overview about what we're going to cover today. We're going to just first dig into a little bit about what Containerd is and why I think it's interesting. We're going to talk a little bit about Containerd's architecture and how it's designed in a very modular way. We're going to cover the different extension points that are available for customizing its behavior. And then we're going to have some examples and a little bit of a demo. So the first thing that I want to talk about is Containerd itself. I hope that if you're at this talk, you're at least somewhat familiar with containers. Maybe you've heard of Docker, maybe you've heard of Containerd. I'm going to be talking mostly about this Containerd runtime today. It's a maybe a little bit less known container runtime. It's small and focused, has a very limited scope in terms of its design so that it remains very simple. It was built by many of the same people that put Docker together. And they used lessons that they learned from things that worked well in Docker as well as things that were not quite as good in Docker. And so one of the things that makes Containerd different is its limited scope, its strict subset of features that it's going to support. So some of the things that it does do are it does container lifecycle management, it does image management, it manages the container standard I/O streams, but it doesn't do things that are higher level functionality, things like overlay networking, having networks between multiple different machines. It doesn't do clustered storage, so anything with storage where you're sharing between different machines. It also doesn't have any built-in logging features or log collection things, log aggregation. So instead, it's just limited to the basic functionality around how do I run containers and run them well locally. And it's built as a bunch of modular composable pieces that are meant to be extended, and that's the main thing that we're going to talk about today. One of the interesting things about Containerd is it's designed to replace some of the functionality from Docker. So it is used by Docker, and Docker uses parts of it, but not the whole thing. This modularity allows Docker to gradually move over to the parts of Containerd that are available. And over time, that amount of Containerd that Docker is using has gone up. It also has modularity that allows for new use cases that are not imagined by the original authors of Containerd. And some of the examples that we're going to touch on today are new use cases that were not originally part of Containerd's design. But before we dig into that, and before we dig into some of the architecture, I want to talk a little bit about images and layers first. So container images are representations of a file system. Docker popularized this concept of a layered image, an image that consists of multiple different parts that are put together to make one union file system. Images are stored, and how images have a copy-on-write view of the different files that are present in the file system. So you can see 3 different layers here. There's a bottom or a base layer, which has marked as read-only. There's a middle or an intermediate layer, which is also read-only. And there's a top layer, which is marked as read-write. If you look at the diagram, you can see that there's a few files on the bottom, there's a file in the middle, and then another few files on the top. And there's some connecting arrows here that are trying to show you where the files are coming from. So if you look at the file that's in the base layer and it's connected by the green arrow to the top layer, that's a file that is unmodified from the base layer and is visible in the top layer without being copied there. In contrast, if you look at the one that has a blue arrow, there's a replacement in the intermediate layer. So it hides the original copy of the file that's in the bottom layer, and the top layer only sees that replacement. There's also in the top layer a brand new file that's not present in any of the other layers. And finally, there's a file there with the no sign that's a deletion marker. So the middle layer is hiding that file from existence, the top layer can't see it at all. The properties of how these work give you copy on write functionality. So when you open a file for writing, it gets copied up into the appropriate layer and it can be modified. But this gives you efficient storage for sharing layers between container images and sharing layers between containers. The way that it typically works when you're running a container is you allocate a new empty read-write layer on top, and only the files that your container is going to modify end up being stored in that layer. So the reason that I wanted to talk about how images and layers work is because the first two pieces of Containerd architecture that we're going to talk about are relating to images. So there's a diagram up here about the different parts that make up Containerd architecture. And these are independent pieces that are meant to work well together, but they can also be composed and replaced and used separately. So we're going to dig into a couple of them that are related into images first. The first one is what's called the Containerd content store. This is where raw image content is stored, or the raw layers. When you go and pull an image into a container runtime like Docker or Containerd, it's typically pulled as a series of compressed tarballs or compressed archive format that's not directly usable on disk. It's going to have to be extracted, it's going to have to be written into the file system somewhere, and there may be some sort of transformation step that enables the copy on write functionality to happen. The content store isn't really concerned with that. The only thing that it stores is the original archived copies of the layers. The next part of being able to actually use images and use layers is being able to lay them out on disk and interact with them in that copy on write functionality. And that's the role of the snapshotter. If you've used Docker before, you've seen what it calls its storage or its graph drivers. The snapshotters are basically the same set of functionality. The final bit one of the final bits of Containerd that I want to talk about is how you actually run containers. Containerd dispatches to a lower level container runtime. This is something that is responsible for actually starting up the processes that make up a container and configuring the parts that are necessary for it. The default that Containerd uses is something called runc, which is the reference implementation of the OCI runtime standard. Runc implements Linux containers, and it does so using a bunch of primitives in the Linux kernel, things like cgroups, namespaces, seccomp capabilities, and so forth. Containerd supports a couple different kinds of runtimes. So one is that it supports any valid OCI runtime, anything that adheres to the same interface as runc. And it also has its own separate version 2 of a runtime interface. The last bit of Containerd that I want to talk about is the gRPC API. This is the central interaction point for Containerd, and it's responsible for mediating the interaction with each of the different parts that make up Containerd. The typical use case for using Containerd is by a higher level program, not interactively, and so the main design is around this API and how that higher level program can interact with it. There's also a higher level client library that's built on top of that API that coordinates actions between different parts of the Containerd API, and is responsible for implementing common workflows, things like pulling images and running containers. So Containerd's overall architecture is that of a modular core built of small separate services that are designed for extensibility. And the way that you use it is that you use these different parts together. Interactions are typically modeled as interfaces in either the gRPC API or interfaces in that higher level client library. And there's a set of plugin mechanisms or extension mechanisms that make it easy to customize the behavior when you want something a little bit different. So now that we know a little bit about how Containerd works, we can talk about the extension points and where it can be customized. So there's 5 basic extension points for Containerd. There's a thick client library in Go that we talked about before that models interactions as interfaces. And you can swap for different implementations inside the client when you want to have different functionality. There's also what I like to call command line or executable plugins. These are programs that Containerd executes for you, and you can configure Containerd to run a different program in place of the one that it runs by default. Containerd also supports gRPC proxy plugins, which are, again, separate programs that implement an entire set of Containerd's APIs, and Containerd is able to delegate out to those programs when it needs to invoke that functionality. Containerd has the ability to load dynamically linked Go plugins. And if you need something even more powerful than that, you can build in your own compiled plugins into Containerd, and you can have your own version of Containerd. So I'm going to talk through each of these. First thing that I'm going to talk about is these client library extensions. So Containerd is built for programmatic interactions, and it has this smart client or thick client in Go that models a bunch of the higher level functionality that most clients are going to need. These are things like being able to pull images into Containerd, or being able to run containers or manipulate them in certain ways. These common workflows are modeled as interfaces in the client library, and they can be swapped out for different implementations when you need something different. So I want to dig into the pull workflow. Containerd is a little bit different from some of the other container runtimes you might have seen. For example, Docker has a simple pull API, and then Docker goes and does all of the networking for you to make that image appear locally on your system. Containerd doesn't do that. The actual Containerd daemon itself doesn't really know anything about the network. Instead, pulling happens as part of a workflow in the client library, and it's the responsibility of the client program to handle all of the things that are involved in making the image appear locally. So there's a default implementation in that client library that can handle talking to Docker registries or OCI registries, and that's what most people are probably going to use. It's what most people are probably going to need. But it is easy to customize if you need something a little bit different. For example, if you want to have Docker-style bare image names, like I want to pull Redis, but you don't want to pull it from Docker Hub, you can define your own implementation of the puller in here to go and resolve that from your own network location that is not Docker Hub. Or you could do things like, I want to customize the TLS settings or the timeouts that are involved in the network transfer. Or if you want to have some completely different protocol, like implement something with BitTorrent, you can do that as well. One of the things that I've done at Amazon is worked on an implementation for Amazon ECR, which is Amazon's container registry, and exposes its own API that's a little bit different from the Docker registry API. And so we're able to write something that takes advantage of the way that ECR works and makes it a little bit faster. So what I'm going to do next is show you a little bit about what the code looks like. So this is how you can write some code to pull an image using the default implementation in the Containerd client. You can see there's that client object, and there's a pull method on it, and there's a few arguments in here, like the name of the image that's being pulled, as well as something telling it that I want to unpack the image. But there's just a couple things here, and it's very simple. But it's also open for customization, and there's a reason that there's some empty lines here. We can go fill those in here, and you can change that to use a different resolver. That's the implementation of what Containerd calls the thing that implements that pull workflow. So you can see here that the only real differences are I'm constructing my own resolver object, I'm passing that resolver to the pull function, and then I've changed the identifier for the image because this particular resolver requires that format for it. So it's pretty simple to go and swap out and use your own. But what does it mean to go and build your own? So this is what the resolver interface looks like in that client library. And this is the interface that you would implement if you want to go and build your own resolver for Containerd. It has three different methods. The first one is the resolve method. This is responsible for returning a canonicalized identifier for the image, as well as what Containerd calls a descriptor. The descriptor contains things like the expected digest of the thing that's being pulled and the media type that's going to be pulled. That's used in other parts of the subsequent parts of the workflow. There are also two other functions here called fetcher and pusher. Fetcher returns an object that knows how to retrieve content, and pusher returns an object that knows how to push content. So if you want to implement something that goes and deals with images in Containerd and deals with remote registries, you would implement at least a fetcher in order to pull something. And if you wanted to be able to push as well, you'd also need to implement that pusher. And so each of those are also returning interfaces. This is what the fetcher interface looks like. This has a single method here. It takes the descriptor object that was returned out of the resolve object and is able to use that to know how to retrieve whatever is being referenced. And this gets called a bunch of different times for a bunch of different descriptors. Typically, the first descriptor that is going to be returned by that resolve method is the one that's going to describe either the index or the manifest of the image. And then the content of that is going to describe the next descriptors that Containerd needs to retrieve. So the things that relate to the configuration of the image as well as each of the individual layers. And the fetch method is going to get called once for each of those different objects. It returns a standard reader object, and that reader is basically going to hide whatever the networking implementation is from the thing that's going to read the image. So as long as you're able to implement your networking as a reader, you can have your own thing go on here. For the ECR resolver that we wrote, we have a fetcher and a reader that's able to retrieve layers in multiple parallel requests for different portions of the content. And just based on ECR's architecture, that ends up speeding up the image pull a lot. If you're going to push images, you need to implement the pusher. So this looks very similar to the fetcher. The difference here is that it's returning a writer instead of a reader. But the same thing applies, that the writer is the thing that's going to implement whatever networking or protocol implementation you want to do. And so you can have your own implementation here that does whatever you need it to do. In ECR, we actually have two different ones, one that relates just to the manifest of the image, and one that relates to the arbitrary blobs, so the content and the layers. Before I move on, are there any questions on this? OK. I'm not going to stop too much for questions in the middle. I'm going to hold most of them for the end. But if you have something burning, please feel free to raise your hand. So we just talked about extensibility in the client library. I want to talk about extensibility in the containerd daemon itself. So the containerd daemon supports what I call command line or executable programs that are invoked by containerd in order to perform some well-defined task. And they conform to some convention that's specified there. And containerd has some different use cases for it, and those have different conventions around them. Things like runtimes and log forwarding. I want to dig into runtimes a little bit. So containerd delegates control of the actual running of containers to another program. And that runtime is able to handle the implementation of what makes a container happen. The runc implementation that's used by default implements Linux containers with the various Linux container primitives, cgroups and namespaces, seccomp capabilities, so forth. But you don't have to do that. You can have your own runtime that does something different. So for example, at AWS, we have this virtual machine monitor called Firecracker that's meant for very lightweight micro VMs. And we were able to implement a runtime for containerd that runs containers inside these VMs. And we're able to do that by conforming to the interface that containerd specifies. And you can see here there's two different interfaces up here. The one that's used by runc, which is the OCI standard, specifies things like the command line arguments, the working directory, files that are expected to be processed. And then there's the containerd v2 version of that, which specifies all those and in addition has an API that you're expected to expose on a Unix domain socket. So how do you build one? The first thing that you're going to do is you're going to build a binary, and that binary needs to be prefixed with containerd-shim-. And that's just something that containerd is going to look for, a binary conforming to that name. It does this primarily to make it so that when you're examining processes on your system, you can figure out which one is the container runtime. You're going to locate that binary in the search path. When you go and run them, containerd doesn't allow you to specify the full file path of the binary, but you just specify the name of the runtime, and containerd will transform that into the name of the binary and look for that on the path. You need to support a couple different command line arguments, things like start to start up a new container and delete to go and delete one. And there's some semantics around how those command line arguments are expected to be processed. So when you go and start a container with these container runtimes, it's expected to write out to its standard out a file path where the API that it's exposing is listening. There's some really nice properties around this model because this means that the container runtime is in control of its own decisions for how it wants to architect things. For example, if it wants to run a separate container runtime process for every container, or if you want to run one container runtime process for all containers, or if you want to group them together by some means, the way that you indicate that is choosing which socket to return. So if you want a brand new process for every container, you just return a new socket for everything. If you want to share, you return an address for a socket that's already existing. And then there's a command line argument for delete where you want to clean up the resources that are used by the container. And the thing that you need to expose over that socket is an interface called the task service. This is one of containerd's, the surface areas of one of the APIs. And this is how containerd controls the containers that are going to run there. So this is what that interface looks like. I've cut out a few methods, but it's a pretty long interface. All of these things correspond to different parts of the container lifecycle and the container runtime lifecycle. Some important ones relate to just how do you create a container. There's an API called create that lets you specify things like the root file system that the container is going to use and standard I/O and a bunch of other options. There's a start method where you want to actually start the process that corresponds to that container. There's a wait method that's available to wait for a process to exit, and so forth. One of the good things about implementing these, though, even though it sounds like a ton of work, there's actually helpers to make it really easy. So these helpers handle things like processing the command line arguments for you, allocating and starting up the service on that API socket, and lets you just focus primarily on your implementation of the interface rather than focusing on the mechanics around how do I get it running. So this is a little bit of what the code would look like to build your own runtime adhering to this interface. There's a main method at the top, and then there's a little helper in there called shim.run, and that's the helper library that Containerd is providing to you that takes care of all that stuff. And the only thing that you're going to do is provide your implementation. There's that thing called myshim there. It's the function that returns your implementation of the task service, and you can make that do whatever you want. So once you've built the runtime, you probably want to test it out. The main way that you're going to interact with Containerd is via its API or the client library. But when you're developing and you haven't necessarily built your client or you want to test with different clients, there's a development helper called CTR, and you can use this to go and test your runtime as well. And so this has a -- runtime argument that you can specify the name of your runtime. Containerd is then going to search the path, find it, execute it, wait for the socket to be available, and run against the API. So that's executable plugins. Next thing that I want to talk about is the gRPC proxy plugins. These are very similar to runtime plugins in that you're going to have a separate program that's responsible for implementing some sort of functionality. The difference here is the different parts of the API that are able to be supported, as well as these are not expected to have a lifetime that's controlled by Containerd. Typically, you're going to run the process ahead of time and configure Containerd with the address of the API that it's going to talk to. So there's a couple different types of proxy plugins. Just the snapshotter and the content store. We're going to talk about snapshotters today. If you remember, at the beginning we were talking about images and layers. Snapshotters are the part that's actually responsible for making the unioning happen, making the copy on write functionality work. There's a bunch of different ways to do that, different implementations that trade off things like speed or space efficiency, or working well with large files, or working well with a lot of small files. Those can be things like the overlay snapshotter that uses the Linux overlay file system to just make files appear as a union together that are stored in different directories. You can have things that are file system specific, like the Btrfs or the ZFS snapshotters that are using native features of those file systems. Or you can use something that pretends to be a block device, like Device Mapper and LVM. So when we were building Firecracker Containerd, the runtime for running micro-VMs in containers, or running containers in micro-VMs, we were able to implement our own snapshotter as a block device-based snapshotter out of process in a gRPC proxy plugin. That snapshotter was later contributed upstream to Containerd, and the amount of work to convert something that was out of process to something that's native in process was actually fairly minimal. So what does it look like to go and implement your own? Again, there's an interface that you're going to need to implement. This is the snapshotter interface this time. And there's some helper packages for Containerd that are going to make it pretty easy to do that again. This is what the interface looks like. This is the thing that you're going to implement to make your own snapshotter. This one's a lot shorter than the other interface I showed earlier, so these are all of the different functions that are there. A couple things to look at. One is called prepare. This is responsible for creating a new snapshot or creating a new layer and making it available for reading or writing. This is going to return a set of mount commands that Containerd can run in order to get access to whatever's to write access into that snapshotter. There's commit that is used for sealing the snapshot once it's been written. And so once a snapshot has been committed, it's not expected to be changed again. Then committed snapshots are able to be used as parents for the prepare call. And so you can have a series of snapshots on top of each other. And this is what happens when layers are unpacked. So you'll unpack the base layer, you'll commit that, then you'll prepare a new snapshot from that base layer, unpack the second one, commit it, and so forth. This is also called when you're going to go ahead and run a container, because you want to create the new empty read-write layer that the container is going to use. And so containerd will call the prepare function again and get a new writable snapshot that's available for the container. You need to configure containerd to know about where to find the address for the plugin that you're going to use. And that looks like this. This is the configuration file that containerd uses. It's a TOML formatted file located in the etc containerd config.toml file. And you can see here that you're specifying the name of the plugin, the type of the plugin, and the address where the API is exposed. And again, you probably want to be able to use this. So typically, you're going to use it through the client library or the API, but when you're developing, you might want to use this CTR tool, and there's a -- snapshot or argument that lets you specify that you want to use that. So there's also Go plugins, dynamically linked Go plugins, and this is a functionality that's in the Go programming language itself, and containerd just built support to import those plugins. It lets you add code into the main containerd executable without having to build your own copy of it. And so it makes it really powerful to let you do really fun, interesting things there. But there's a bunch of complications around it. And these, some of which are similar to pretty much any kind of shared object or dynamically loaded library, things like needing to be architecture specific and operating system specific. But there's also some things in here that are difficult just because of the Go programming language. And those are things related to needing to use basically the same build environment to build the main binary and your plugin. That's because the versions of the compiler needs to match exactly, the versions of the standard library need to match exactly, and all of the libraries that are shared between your plugin and the main application that you're trying to load it into need to be the same. This has to do with like symbol resolution between the different binaries. They have to have the same, they have to be able to resolve the same symbols. So we tried to do this for Firecracker containerd. We have an API that we wanted to implement on top of the containerd socket, and we tried to do that using a dynamically linked Go plugin, and we found that the complications with Go involved in dynamically linked objects just makes it really difficult to do. So instead, we did a built-in plugin. This is the last bit of extensibility that containerd has, the last bit I'm going to talk about right now. So this is responsible for when you want to build your own version of a containerd of containerd. And there's pretty much all of containerd's functionality is actually modeled as these built-in plugins. So the modularity of containerd extends into the core itself. There's about 30 embedded plugins in the 1.3 release of containerd. And those are things like the default implementations of the snapshotters and the default implementations of the shims to talk to the runtimes, various components for orchestrating different parts. And every component can be extended, replaced, removed. The downside is that it requires you to build your own binary. The good thing about it, though, is that just like containerd's made other extension points really easy, it's made it really easy to build your own binary that doesn't involve you forking containerd. Instead, because all of containerd's functionality is pretty much these plugins, and they're all exposed as Go packages, you can treat containerd as a library. And you can basically write your own main function, import all of the things, and then you have your own version of containerd that has your own mix of what things are supported. I like to call this a distribution of containerd. So how you do that is you're going to write your own main function, and you're going to hook into containerd's plugin system. And this is what it would look like. Here's a main function. I've got the command.app thing that I've imported from containerd, and that's the plugin system that's responsible for loading and running all of the plugins. Then you're going to import all of the things that you want to load into it. And these are imported as Go plugins, or as Go packages. So there's a pretty long list of what the existing ones look like. You're probably going to want to use most of these. If you look pretty closely, you can see that there's some of the things that we've talked about. So the content store is on here. There's also an images thing that deals with metadata around the images. This is about half the list, and the other half is over here. And this also has some of the things that we talked about. There's the snapshot service in here. And you can see at the bottom, I've imported my own into it. And so I can have my own plugin that is also imported in the same mechanism. If you look at the way that these imports are, and if you're familiar with Go, you can see that all of these are imported as underscore plugins. Go enforces that when you're importing packages that you reference the symbols in them, except when you import them as underscore packages. And that means basically you're importing it for the side effects. So what do I mean by side effects? Well, Go lets you specify a special function called init that runs at the time that the package is imported instead of being called directly. So the nature of all of these things being underscore imports means that the init function is going to run. And so you'll want to write your own init function that handles registering your plugin with containerd. And this is what it would look like to do that. So here's my init function, and I'm going to call containerd's plugin.register API and specify things like what is the name of my plugin, what is the type of the plugin, do I have dependencies, as well as yet another init function embedded in here. And containerd will take care of making sure that all of your dependencies are imported and running before it calls your init function here. So this is basically it for how you do that. So the next thing that I have is a little bit of a demo. And let's see what goes on here. So can everyone read this? OK. Just going to flip to my notes. So I have here just an EC2 instance that's been loaded with a couple things. So it's been loaded with containerd, it's been loaded with the various extension points that we've been talking about for doing things with ECR and doing things with Firecracker. Oh, I should maybe start the demo. So if we look here, we can see these are the different things that are available on there. You can see that there's Firecracker containerd listed there. That's my custom distribution of containerd. I've also got something there called ECR pull that's going to be responsible for pulling images using the resolver that we wrote. There's that CTR command line tool that is just basically a debug and development helper for containerd. And I've got a couple of these containerd shim binaries, some that correspond to runc, and one that is listed as Firecracker, and that's the one that uses the implementation that we've written. And I'll show you a little bit about how we've configured containerd. So it looks pretty much like a regular containerd configuration, except that I've told it where to store its state and where to expose its socket, and also that I'm going to use the device mapper snapshotter by default. This is the one that we had originally written as an out-of-process gRPC plugin, but now it's built in, and so I can reference it just like this without having to specify its socket. And what I'm going to do now is I'm going to look at the images that are present. This is just using the CTR command line tool, and we can see that there are no images. So I want to go ahead and pull one. And I'm going to use that ECR pull binary. This is using containerd's API to go and pull the images. So it's that pull function that we looked at before. And it's also got our special resolver that knows how to pull from the ECR API instead of from the Docker API. And we can go ahead and pull that. And then it gets unpacked. And we'll go ahead and look at this again. And you can see, even though I'm using the CTR tool and I use the ECR pull tool, they're basically showing the same content. So the CTR tool now shows the image that we pulled. And let's see what it looks like to run it. So if you're familiar with containers, I want to show you a little bit about what the host looks like and what it's going to look like inside of a container. So the first thing we're going to do is I'm going to show you about the host. You can see this is a Linux kernel. It's got a host name that looks like an EC2 instance because it's an EC2 instance. It has the Debian cloud kernel loaded onto it. It's also, the OS release file tells me that this is a Debian instance. And so what we're going to do is we're going to run a regular container, a regular Linux container first on top of this and use the Amazon Linux image. And we're going to look at the same things. So we look at this again, and you can see it's the same host name, it's the same kernel. It's actually shared, and it says it's Debian, even though this is an Amazon Linux image. I promise I'm a faster typer when I use two hands, but I'm holding the mic. And then you can see here that this is reporting an Amazon Linux image. So this, if you're familiar with containers, you know that they typically share a kernel, and they're just running as processes and a user land on top of that kernel. So this shows us that we're running the Amazon Linux user land on top of the Debian kernel, which is what I would expect from a normal Linux container. So we'll get out of that, and then we're going to do basically the same thing, but we're going to specify our custom runtime here that runs it inside of a Firecracker micro VM. And so we've started up a virtual machine now, and we should see something a little bit different. And you can see that I've got something different here. I have a different host name that's reported. I've got a completely different kernel version that's reported. And this is showing me that this is the Amazon Linux kernel, not the Debian kernel. So even though I'm using a Debian host, I'm running a virtual machine inside of that, and then I'm running a container inside of that. And we can look, again, to see what the OS release file looks like. And this is going to show you the same thing that we saw in the image before. So it's still a regular container. It looks like a regular container, and it's just running inside of a virtual machine using the custom runtime that we wrote to extend containerd. OK, so you can see what it looks like inside the container. Now I want to show you a little bit about what it would look like to run a regular container and then a Firecracker VM with a container inside on the same host. So we're going to start up one of these again. This is, again, a regular Linux container. Not using our custom runtime, and it's just running sleep in the background. And so when you run containers on Linux, you can typically see the process that's running, and so we should see a sleep process here. And we can go look at the processes that are related to this one. And you can see that this is a sleep process, and it's got some namespaces associated with it, and it's running under the containerd shim. This is the thing that's implementing the runc stuff, and that's parented under systemd right now. It's just related to the process model that's used for that particular implementation. So we'll go ahead and kill this, and then we're going to do the same thing, but we're going to run it inside of our custom runtime, inside of Firecracker. And so this is, again, going to start up a virtual machine, and I actually wouldn't expect to see the sleep process now, and I don't. Instead, what I can look for is the Firecracker containerd process. This is our distribution of containerd, and I can look at the process tree that's associated with that. And now you actually see that under this are some Firecracker processes and a containerd shim that corresponds to the Firecracker process instead of the runc process. And so that's pretty much what the demo looks like. Recap of this, we just showed a couple of extension things with containerd where you can write your own resolver and you can pull images not using the default one. We showed that we have a custom containerd binary, a custom distribution of that with some extra functionality built into it. We showed the device mapper plugin. That's the thing that uses block devices. And that was just used for in our containerd configuration file. And we showed the containerd shim, the implementation of the runtime used for micro-VMs. And so at this time, I'm happy to take questions. So I'm going to try and repeat questions because I think we only have one mic. And so I am going to ask you to speak up so that I can hear you up here. But for anyone that didn't hear, the question was about whether you can run privileged containers inside Firecracker, Firecracker containerd. So yes, this is it runs a Firecracker containerd runs by running a virtual machine and then running containers inside of it. And so you can run containers that are privileged in the context of that virtual machine. And so they can have full control over the host as if they were, because they just see the virtual machine instead of seeing the outer host. Any more questions? No? OK. So I'm going to be around after this. If you didn't want to speak up in front of everyone, but you still want to come ask me questions, I'll hang out right here after this. I'm also going to be around the conference the rest of the weekend if you want to come find me. My Twitter handle and my email address are up on there if you're not comfortable approaching me, or if you want to, if you don't get the chance to. I don't know that they're doing session surveys at this conference, but I would appreciate your feedback, things that you liked, things that you have constructive feedback on improvements. I'm sure other speakers would probably appreciate constructive comments as well. Please remember that everyone here is a human, and so please adhere to the SCaLE code of conduct with your responses. And just thank you.
Yeah. Didn't that suck? Fun times. I told them to change this out. Hopefully they changed it.
We were just hoping.
Test, test, 1, 2, 1, 2, 2, 2.
I mean, it's fine for me, yeah. That means that I guess we lost some.
Mic check, 1, 2. Testing. Test, 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 test. 1, 2.
Hey, everybody.
Wait, you just dropped the pop filter off.
The what?
The pop filter. It was on top of the mic.
There we go.
Damn. Here. We need some glue. Okay.
Do me a favor, put that in your pocket. Or at least
Yeah, first let's see if this is working. Is that okay? Is it good? Okay.
Or on your pocket, whatever.
Oh, so you know what though? I have to prevent further problems. Wow, it's just, I don't know what this is. This is just hypersensitive. Oh, it fell off again?
Fine.
Well, I mean, it hasn't been working. That's why we had to give up on using it before. Okay. Hopefully that's better.
Put it on the same side, just out of so it doesn't go across your body. And,
Okay. Okay. There we go. Hopefully.
Yeah, we don't like to interrupt the talk. Sorry about the losing the slides. We don't like to interrupt the talks when
Yeah.
we're not recording because
Yeah.
there's people in here. You guys are the most important.
Right.
Not the people out there.
Okay. So.
By the way, I'm a pendant. You may figure that out.
Yeah.
That is not a lavalier. That is in fact a Countryman or a headset microphone and not a lavalier. Because technically
Okay.
a lavalier is a different kind of microphone.
It's right, yeah. Okay. Mhm.
Do you feel good about it? I can just trade out the whole mic.
Yeah. Okay.
Test, 1, 2.
Okay. Yeah. Also, this one hasn't been bent quite so many times. Okay. How's that?
Oh, that's so much better.
Oh yeah. Okay.
All right, great.
Cool.
A friend of mine who's at work is trying to view this at the site, mentioned he's having problems with the slides. That's about 30 minutes ago.
Yeah, they were having a video problem that should hopefully be resolved now.
Okay, should I ask him to retry later on in the evening maybe?
Hold on.
So hello, everyone. Welcome to the Containers and Virtualizations track. My name is Elizabeth. I work at IBM, and I'm one of the track chairs for this track. I'm pleased to introduce one of my other track chairs here, Josh Burkus. He works at Red Hat, which means I guess we work at the same company now. But he's here to talk about, as you can see, how fast was my cluster. Thanks.
Thank you. So howdy, everybody. I'm going to talk about something that people have not, have not actually talked about a lot in Kubernetes world until very recently, which is performance. And I mean, a lot of it just has to do with we've been spending a lot of time building up functionality, and performance is irrelevant if you can't do the things you wanted to do in the first place. And so now we're getting to the point of being able to do all the things. We're looking at other areas. But first, I want to actually make a little disclaimer, just to make sure that nobody's going to be disappointed and nobody's in the wrong talk. The description of this talk said I would be talking about both own hardware and cloud performance. This talk was slotted in as a last-minute replacement for a cancellation, and I did not have time to integrate my latest cloud performance information into it. So during this talk, all I will have in my slides is own hardware performance. I can take questions about cloud performance, though. So, that out of the way, let's talk about a few things. So, first thing people say is, hey, why are you even talking about this? Isn't Kubernetes just for stateless applications? And there are some people who firmly believe that Kubernetes is just for stateless applications. As a matter of fact, historically, Kubernetes was just for stateless applications. If you started with Kubernetes 1.0 or earlier, as I did, there was no way to get it to work for anything that needed storage without really hacking Kubernetes itself. That's changed a lot. We've added a whole bunch of different things to Kubernetes, both core features like stateful sets and volume snapshots and local volumes, and a whole bunch of plugins and other Kubernetes ecosystem things in order to make Kubernetes an effective orchestrator for applications that need state and storage. And this has resulted in a lot of people moving their stateful applications to Kubernetes. In dev, in testing, and in production. But there's still a few roadblocks. Still a few things that don't work great out of the box, that people run into out of the box as problems. Now, these roadblocks generally fall into three different areas. One is management. That is, how do you manage your storage and your other repositories of state across the cluster, particularly in the event of failover or redeployment or a whole bunch of other things. Second is storage setup complexity. That is, I would say it's not significantly harder to set up your storage in Kubernetes, but for a lot of kinds of storage, it's not any easier either. And it wasn't exactly easy in the first place. And the third is performance, which is what we're going to be talking about today. Now, for storage setup complexity, we've made a lot of progress by extending Kubernetes itself through things like the Rook operator, which does actually greatly simplify setting up certain kinds of storage. For management, UI, UX, that sort of thing, haven't made a lot of progress, sorry. Like I said, all I can say is it's not like setting up storage was easy. It's not like running storage, like running stateful applications, required zero expertise before. But then we come to this last one, performance, which is what the rest of this talk is about. Now, people say, why does performance really matter in this context, right? Just add more servers, whatever. Well, I mean, I will tell you, system administrators, ops staff, DBAs, that sort of thing, they do care about performance because extra machines or extra cloud instances are expensive. And if you need more of them, then it's a problem. there are a whole variety of options, which I will be exploring in this talk, that allow you to trade out various gradations of ease of use for raw speed, which is a trade-off that is familiar to people who work in the ops sphere. How many people here, by the way, are a system administrator or database administrator or ops? Yeah, okay, yeah. So you understand, right? You're always making trade-offs on, hey, this platform is really simple and it's point and click, but it's dog slow. That's the trade-off you always make, and you can make those same kind of trade-offs inside Kubernetes, but you need to know what the trade-offs are, not just qualitatively, but numerically. And then the other thing is, performance can be a migration roadblock, right? Because you have an SLA that you need to meet, and no matter what other advantages that Kubernetes brings to the table, if your database can no longer meet its SLA once it's running on Kubernetes, you can't migrate. So it's an important thing to answer. And so I and a bunch of other people were working on answering. We're forming a sub-project of SIG scalability in Kubernetes to actually address application performance, because we care about this. Other reason I care about it, of course, is that I worked on PostgreSQL for 18 years. I've worked on database benchmarking and stuff. Spent about 10 years in TPC, et cetera. So I'm familiar enough with benchmarking that I actually find it fun. So, oh, by the way, there's that word benchmarking. Let's talk a little bit about that. Has anybody here actually done any benchmarking? A few people. Okay. So for the people who haven't, one of the things I want to say is important about benchmarking and something that people get wrong is they think of benchmarking in terms of, hey, I'm trying to achieve a number, which is actually wrong. Because what you're doing when you're benchmarking is you are trying to compare things. You are trying to say, hey, if I have this on direct attached storage, how does it compare to having it on distributed storage? If I have this running on Kubernetes 1.16, how does it compare with Kubernetes 1.18? If I set this up with 3 copies of each shard on my Ceph storage, how does it compare if I have 4 copies of each shard? And most importantly, how does all of this compare against the SLAs or SLOs I am already required to meet? So what you're really looking for is to take 2 or more things, or a lot more things, and compare them using the benchmark as a tool. Now, I also want to talk a little bit about the types of storage that are available to us in our sort of cloud native environment, right? You have your straight up, you know, I'm just going to use the machine storage. We have some more Kubernetes advanced usage of node local storage, which I'll explain a little bit more about. You have network storage, and again, this is going to be like various things. It can be within a local environment. It can be iSCSI. It can be NFS. It can be something like that else. Within a cloud environment, you're going to always be using network storage. Pretty much all storage in public cloud is network storage. And then we have what we call cloud native distributed storage. The paramount example of which being the Rook-Ceph combo. But this means that your cloud both hosts the storage and provides it. And it has some advantages. And again, talk a little bit more about that later. But these are sort of types of storage. Now, because today's talk is going to be about my own hardware, my hardware setup, I am skipping the network storage part of the comparison. As opposed to on public cloud, where it is all comparison against network storage versus ephemeral storage versus other things. So instead, we're going to compare local storage running off of Kubernetes, on Kubernetes, and then cloud-native distributed storage. Now, I also, because most people haven't done benchmarking of storage and other things before, I also want to explain a little bit about what we're looking at when we look at storage performance. So we have 4 different activities that we can do in terms of the computer system interacting with storage, right? You have random reads, which is get me this 1 block from disk, and random writes, which is write this 1 block to disk. You have sequential reads, which is, hey, I want to read this gigabyte all at once, and sequential writes, which is, hey, I'm going to write out 12 gigabytes of data to consecutive sectors if you're on spinning disks, or who knows where if you're on SSD. And these have notably different behaviors to the point where systems can be faster at one and slower at the other. Depending on what you need out of your application, it's important that you optimize for the kind of storage activity you're going to need. Like, for example, if you're running a small database, you're going to do lots of random reads and random writes, and therefore you want a system that performs well for that. Whereas if you're running, say, video streaming, you're going to do a lot of sequential reads and writes, and it's more important to optimize for that. And some storage systems really do trade that off. So now, because random reads and random writes are so often a combination, read, write 4K, read 4K, generally in benchmarks these are tested together. And so you'll see when I give you the figures, it's a figure together, whereas sequential reads and sequential writes tend to be different activities and separate processes. Now the other thing that I'm going to talk about is there's two different ways that we measure storage and memory performance, right? One is latency, which is how long does it take to start getting results after I make a request. And the other is throughput, which is how many requests or how much bulk data can I move per second, per minute, per whatever. And again, these two things not necessarily vary together. You can actually have systems that have high latency but great throughput, or vice versa. So, 18 different combinations here. We kind of want to test all of this information. Fortunately, there is a large body of tools and information to do this in the form of database benchmarks. Because database geeks care about performance deeply, because they are constantly under pressure from the businesses that they work for to make the database faster. And so they care about performance. And one of the nice things about the database is it tends to actually hit all of the systems. It tends to use CPU and memory and storage all at the same time. Plus, we have all of these different tests that we can use that already give us a very rich set of information about how our system is performing and what kind of actual latency and throughput we're experiencing in different combinations of actions. I'm going to introduce you to a few tools here. There are actually a lot more out there. It's lovely. A lot of them are open source. A lot of them are easy to use. Again, because I didn't have a chance to update these slides for the slot, one of the ones I don't have in here is for a Kubernetes only experience, the Kubernetes benchmarking operator, Ripsaw. Which, if you're only going to check within Kubernetes and not outside Kubernetes, inside Kubernetes, can be a really easy way to do benchmarking of your cluster. But Sysbench is an old tool. Oh, by the way, you're right. Sysbench is an old tool created by the MySQL folks. It does a variety of different I/O tests plus database performance tests. I'm going to show just the I/O tests here because I'm going to show database performance with PostgreSQL's pgbench, which ships with Postgres, which is a transactional database test. And then CockroachDB, when they launched, they released a bunch of these useful workloads based on industry benchmarks. Unfortunately, like other portions of CockroachDB, these are now under a non-open source license. Just if you're using them, you need to look at the license that you're using. We're going to do some checking of direct file I/O with Sysbench. Now, Sysbench does have database tests. It has some other tests built into it. You can see, look at the Sysbench documentation, which is very extensive and has a lot of comparisons for it. If you don't want to use these other, like if you're going to use only one popular open source tool, I would say Sysbench is the one to start with because it does the most things and it's very well known. Postgres pgbench is this database micro benchmark that does a lot of random reads and writes. But one of the things that I can use it for that is not available through Sysbench is I can also time the amount of time it takes to build the initial test database and use that as a bulk load test. And so that gives me my information on sequential reads and writes. The CDB workloads, they had a whole set of database micro-benchmarks. Bank is a lot like PGBench. TPCC was a more complex sort of lock-bound workload, and this is something you encounter. Lock-bound workloads, I think, is something that are fairly unique to the database world, and those are workloads that really scale badly, because the more processes you add to them, the more locks they have. And TPCC is a good example of that, but it also has to measure latency. Now, one of the other things I have to caution you, again, with doing this is, when you are doing your own benchmarking, which is the purpose, part of the purpose of this talk is to get you to do your own benchmarking, right? Because I'm going to show you what happened on my system, on my cluster, but my cluster is not going to be set up exactly how your cluster is. And so you need to test on your cluster. And one of the things you need to remember is you need to do a bunch of runs. Like, don't just do one test run on each configuration and assume that information is good. No, you need to do multiple runs and, like, average them or whatever. They need to be long runs because there's a lot of things like file caching effects, et cetera, that behave very differently with sustained activity. Ideally, you need to use multiple file and database sizes. You want a realistic level of work. So a whole bunch of client connections like you would have during peak load in production. And then I'm going to actually say, if possible, like if your goal is to test the software, then you actually want to do it on bare metal and not on cloud. Now, why would I say that? It's obviously easier to test on cloud, right? You can spin up as many AWS instances as you can afford to pay for and do it in a few minutes, right? Huge advantage. However, there's a problem with that, which is on any public cloud, you have this problem called noisy neighbors, where other people are doing resource-intensive things on sharing the same physical hardware with you. And the important thing is you don't know how many people and how much activity they're doing. And so often what looks like a difference in performance is actually a difference in overall cloud load. So if you are running this on bare metal, you can do fewer runs and have more consistent information. Like, and the difference is, for the benchmarks you're about to see in bare metal, I ran each one like 5 to 10 times. For the cloud stuff that I've done, I have to run it 25 to 30 times over a period of days, because I have to make sure that I'm not getting stuck in, say, a bad rack in Amazon's data center somewhere. So you can also do larger sizes because, I mean, let's be frank, 128 gigabytes of memory in your own hardware is like a bare minimum for a server machine, whereas it's very expensive on an AWS instance. So all of those prerequisites out of the way. Does anybody have any quick questions about the sort of parameters of benchmarking before I go into results? Go ahead. Yeah.
Bring you the microphone.
Like tools you're using, they're obviously like you didn't write them, we didn't write them, and we don't know all the. So the tools that you're using, you didn't write them, we didn't write them. We don't know exactly how they work, and so it's possible there's like CPU pegging or NUMA problems or like any number of things could be causing contention rather than actual storage issues. How do you like isolate?
Well, that's the reason why I strongly recommend that you use open source benchmarking tools and not closed source ones, because then you can actually look at what the code is, because absolutely that has happened with benchmarking tools. And it's not necessarily intentional on the part of the benchmark designer. They just took advantage of what seemed like a shortcut to them and ended up, for example, pegging all the activity on CPU 1. But that's why you need to use open source tools so that you can actually look at that. And that's actually also the advantage of using some of these older, better tested tools rather than the brand new ones. I mean, that's the disadvantage of using something like, say, the CouchDB tools or the MongoDB YCSB benchmark, which I do use because it tests a different use case, is that they're just very new, and some of those issues have not necessarily been worked out. And you might have to work them out. Okay, so let's talk about some results for comparisons. So one of the things I want to caveat here is that people like to want to publish results and stuff. You know, if you're going to go for a benchmark publication, there's a whole long process for that. I used to be part of an organization called the TPC, and it would take like 6 months to do a benchmark because we had to make absolutely sure that the results that we were getting were comparable in an absolute way. None of the results that I'm giving you are comparable in an absolute way. The different tests are not comparable with each other because they have different code and different parameters. The different databases are not comparable with each other because that wasn't my goal. You can set it up so you're benchmarking databases against each other, but that wasn't what I was doing. The databases that I'm using here are minimally tuned, basically out-of-the-box configuration settings, which is not ideal for database testing, but again, I wasn't looking to test the databases. And of course, my hardware and software is going to be different from yours. So let's talk about the hardware that I was using for this. So I have a 6-blade cluster in Red Hat's open source lab. Each of these blades has 20 cores and 128 gigabytes of RAM, and 2 SSDs that are 200 gigabytes-ish each, and a shared network. Now, this setup immediately puts some limitations on my testing. First of all, one of the things I really like to do is I like to test a workload with a small database, and by small, a database that is substantially smaller than RAM. And then I like to test a database that's big, which is a database that is substantially larger than RAM, to force things like swapping on the system. And because my RAM is almost as big as my storage, I could not really do the second kind of test. I kept running out of disk space when I tried. I am going to reconfigure these machines so that I can actually do that kind of test, but I haven't done it yet. The other issue that limited me was the shared network, which I will talk about in a minute. But what this means is, because my databases all fit in memory, it means that my primary limiter was going to be file sync I/O rather than raw write speed. Now, synchronous I/O is what you do in order to make sure your data was saved to disk, right? Lots of applications do this when they need to know that the data got to disk. All transactional databases do it. A lot of storage systems that care about missing data, like video systems, do synchronous I/O in order to make sure that it gets to disk. So it's an important thing to test, and that is what I ended up testing for a lot of these. The shared network also was an issue, like I said. So now, my first test is what I call the bare metal test, which is a pure host file system, as in Kubernetes was installed but not running. And I ran the benchmark client and the database on 2 different machines, 2 different blades, not in containers or anything. And so this is to get my reference number, right? If somebody is looking at migrating from bare metal from own bespoke server to running on a Kubernetes cluster, that's the comparison they want to make. And so I wanted to make that comparison. For anybody who cares about this, using XFS on LVM for file system, etc., obviously, as always, has some effects, but it's a fine combination as far as I'm concerned. So, going to give you the grid layouts. So I'm going to show you a set of results for these, and I've put them in grid to make it sort of easy to visually compare them. And so this is for the sysbench, and I'm just using the sysbench file I/O test in order to do a random read and write combination, sequential read, sequential writes in this grid. So for the raw system here, these are again large memory, SSD storage, random writes very fast, random reads. Both random reads and writes are very fast. Sequential reads are really, really fast. Sequential writes were not very fast for reasons I still haven't determined. I actually ended up doing this so much as, in fact, reformatting one of the machines, reinstalling the OS and stuff to figure out why this is going on, because that's a low number considering the hardware that I have, and I have not yet figured out why it's that low. But the purpose of this was to get comparisons. Now, here's my second grid here, and this is 3 of the benchmarks, database benchmarks. So we got PGBench across the top. We have the bank benchmark with CockroachDB. and the TBC benchmark with CockroachDB. And I didn't actually say earlier, one of the other reasons I want to run the CockroachDB benchmarks is Postgres is a single node database or a fully replicated database, whereas CockroachDB is a sharded database. And so there's obviously some different performance there. Single node databases have more limitations on how much they can scale up in terms of CPU and storage, et cetera. Sharded databases use a lot more network. And so you want to test both of those cases. So we did bank and TBCC on CockroachDB. For pgbench, we have the simple thing DB load time to look at a big sequential write, transactions per second, and average latency. Bank is actually kind of the same things. The nice thing about the bank test with CockroachDB is it actually gives me a percentile instead of an average. And a percentile is always better because SLOs and SLAs are generally expressed as 95% of transactions must complete within X. And so that's the number you actually want to know. Now TBCC, that new orders per second you'll see doesn't change much because, again, this is a lock-bound workload. And so that number only changes if the actual storage or memory or whatever hardware is slower than clearing the locks because people are not allowed to buy the same merchandise at the same time, right? For obvious reasons, right? It's an online store, you run out of things. So you have a real problem if you don't meet the SLO for new orders per second. And you'll see it actually doesn't change a whole lot in this particular run of tests. So for bare metal, for pgbench, 404 seconds to load the initial database, including index builds. So that's my bulk load time. 11,000 odd transactions per second, a 2.8 millisecond latency. Now we've got a blank right here, and what's going on there is I have a fair amount of experience running CockroachDB on Kubernetes. I don't have a lot of experience running CockroachDB off of Kubernetes, and the numbers I was getting running it on bare metal were so bad, I clearly set it up wrong. So I don't want to share those numbers because they're not indicating anything. So I'm going to compare against the different Kubernetes configurations for CockroachDB. So we're going to do our first comparison. So there are a couple of different ways to use local volumes within Kubernetes, where what you're doing here is you are attaching local storage, local to the node something is running on, directly to the container running within Kubernetes. Local PV is the more sort of sustainable way to do it. There's still a bunch of it's a relatively new feature though, and so there's some kinds of storage it doesn't work with. And so some people are still using the older host path, which is harder to manage, which is why you want to use local PV if you can. These are two different sort of Kubernetes constructs. Basically, these are just local storage via container. So theoretically, since a container is just an abstraction in the Linux kernel, it's not a real thing, theoretically this performance should be nearly identical to bare metal performance. Let's see if it is. Well, for the raw file I/O test, it is, right? Less than 1% difference with anything, which is, so you can see there, and given the amount of variance in these tests, less than 1% difference really means no difference at all. The tests are not that consistent that you can actually measure at that level. Now let's see the database tests. Now that's a little bit different. So we did have a longer amount of time to do, we had 10 to, you see here 17% difference on the Postgres test. We're also getting some establishing numbers here for CockroachDB because now I've got a CockroachDB cluster running, so we've got our establishing numbers there. So what happened here, right? This should theoretically have honestly been, the same as we saw. The raw file I/O was not really any different, so why was the Postgres result different? Well, so the thing was, for my bare metal establishing thing, the client, the benchmark client, was not running inside Kubernetes. It was running on a host machine. So to make it comparable, I have the benchmarking client running on a host machine in this test. The problem with that is this means I'm going through some simple Kubernetes load balancing called node port in order to actually connect to the backend database, and this means at least one extra network hop, unless I'm lucky. And you see here the big jump is latency. And pgbench, because it does a lot of really small transactions, latency, it really dominates the benchmark because it's sending all of these little tiny short commands with no batching. And so, but it waits for a command to come back right before it sends the next one. So that network latency hit me particularly because, remember I said that all of these blades were on a shared network, shared with everything else in the rack with them. Well, this is also hitting me at this point because my network for Kubernetes internal communication and the network for the benchmark client communication is the same network. And so it had an amplified effect here. Now, our third configuration that we're testing here is our cloud-native storage using Rook and Ceph. So we've got 5 nodes of Rook and Ceph here. Now, because it's such a small cluster, I only did 2 replicas of each shard of the storage. Normally, for production thing, we have a larger cluster. You would do at least 3 for failure things, but it seemed ridiculous to do 3 when we only had 5 nodes to choose from. I did do some default tweaks that are in the Ceph documentation for performance. And the other important thing is I'm going to show you CockroachDB. So this is CockroachDB running on top of Rook Ceph as its storage, not Rook controlling CockroachDB, which is another option and is the sort of more mainstream one. Because one of the questions you would ask is, hey, if CockroachDB is a sharded replicated database, why would you put it on sharded replicated storage? And the answer is you really probably wouldn't, except for certain special circumstances. The reason I did it in this case was it showed something I wanted to test rather than something that was a likely production scenario. So we're going to go sysbench, and now we see some differences in raw file performance. So random reads and random writes are down a minority percentage, but still a noticeable amount. And again, this is some latency. Every time I write something, it's being written twice synchronously, and so we've got extra network latency, et cetera. So those are actually pretty good numbers if you consider that. Not a lot of difference in terms of reads, which makes sense. And my sequential writes actually went up. And I had to delve into this some. And it turned out that the reason for this was because it's sharded storage and because I was sequentially writing a substantially sized database, the chunks of the database were actually being written to different machines. So I, in fact, gained performance by having the database sharded in this particular case, or having the files sharded. Because what sysbench does is it writes a bunch of chunks, 1 gigabyte chunks, and it writes a whole bunch of them. And so what happened was the different 1 gigabyte chunks were landing on different physical machines, which meant that whatever that 88 megabyte cap was with these SSDs, I was able to exceed that limit. So sometimes using using this advanced storage actually benefits you performance-wise. Now let's look at some of our database benchmark results here. Right. So now we see a bunch of extra overhead, right? We've got about 28% longer for the bulk load. A substantial, basically what we see consistently across this is our latency doubled for all of the sort of database workloads. And the things associated with that latency were cut in half. So latency doubled, throughput got cut in half. And this actually makes sense, right? We're writing everything twice that we weren't necessarily writing twice before. We're writing it twice as much in the case of CockroachDB. So we're doing twice as many synchronous writes with a minimum of 1 extra network hop. So, and I'll actually tell you, I've been testing databases on distributed storage since the days of MooseFS. Anybody remember MooseFS? See, there we go. A couple of people remember it. So since the days of MooseFS, and these are actually really good numbers. Because you think about it, how many databases do you have that actually are already twice as fast as you need because your expectations aren't that high? Right? My Postgres, MySQL, a lot of CockroachDB databases now are actually really, really fast, and often not the limiting factor in overall performance. And so this can be acceptable, but it can be not acceptable if you actually are hitting that limit. So some of the other things I'm tinkering with here is, and actually, if you look at one of the KubeCon archives, look for, within the KubeCon YouTube stream, look for a presentation by a company called Percona. They went ahead and compared the different overlay networks. For this, I was just using the default overlay network for OpenShift, which is Open vSwitch. The different overlay networks actually turn out to make a huge difference in performance, and so do look for that presentation by Percona. I'll sum it up with 3 words, which is don't use flannel. I need to reconfigure the storage so I can actually do bigger databases. I distribute workload over CockroachDB better would be nice. Problem is with CockroachDB becoming non-open source, I'm probably going to stop doing testing on it, which is a shame because it was super useful. And of course, ask the Ceph guys to do some Ceph tuning to see if it makes a difference, except that, like again, from my perspective, Ceph was performing so well, I almost don't feel like it's worth doing any tuning. So, some conclusions here before we go to questions. Number 1 is benchmark your own hardware with simple database benchmarks to test your actual cluster performance. Second is local volume performance can be equivalent to running on bare metal if you're looking at moving to Kubernetes. So if you're willing to deal with local PV, et cetera, if you're performance constrained, that's actually probably the way to go. If you are not that performance constrained, Rook-Ceph has good enough performance for non-constrained applications while giving you a lot of sort of redundancy, et cetera. A couple of others. Also, beware secondary issues that look like key performance differences. Like sometimes your performance difference isn't coming from where you think it is, like my issue with using NodePort and the network between the benchmarking client. And then an extra tip that I'll say, because I didn't have my cloud slides in here, is on public cloud, one of the other things you'll discover is that public cloud latency effects, which are large, can mask any differences in performance that you are attempting to test. So, I am ready to take questions. And like I said, you can ask questions about the cloud stuff. I just don't have it in the slides, but we did do a whole bunch of testing.
Tell us about the cloud stuff.
Tell us about the cloud stuff. So to do the summary is we did so first I did a big test run just using a bunch of Amazon instances using pgbench and sysbench. And one of the things I discovered is using EBS natively, so using EBS via host path, versus using EBS via the Amazon CSI driver, there was no difference. So there wasn't a good reason to use host path for EBS volumes, since the CSI driver does a lot of failover management, et cetera, that you lose when you're doing local PV. So if your data is going to be in EBS, you want to use the Amazon cloud provider stuff for the EBS storage. We did discover that, then we did a bunch of Ceph Rook stuff, we discovered that whether it was better, if your data needed to be redundant, whether it's better to use EBS and rely on Amazon's redundancy versus using local ephemeral volumes but redundancy via Ceph and Rook on your own is workload dependent. There are workloads where EBS is cheaper and more reliable, and there are workloads where Ceph Rook is cheaper and more reliable. And to get more into that, I have to get into the numbers, but it's a sort of reasonable trade-off. We're going to actually, Saggy and I are going to blog about that particular issue, because we've also done cost comparisons, which are obviously a big deal in the public cloud. That's sort of a summary of the cloud stuff. More questions? Are there any limitations on the size of a database in Kubernetes? There aren't any specific limitations. The one thing I will tell you is Kubernetes thinks of itself as a sort of multi-tenant system, and therefore when you get to the point where a single pod is going to be using more than 50% of the resources on the system, you find yourself having to tweak Kubernetes for a lot of non-default behavior. So my general advice for people who say, should I run my database on Kubernetes, is to the extent that you have a lot of small databases, yes. To the extent that you have a few really large databases, no. Unless those databases are weird distributed sharded databases, in which case you can go back into Kubernetes land simply because for some of the sharded databases, Kubernetes effectively makes a great installer. Other questions?
I don't know if you said this or not, but is your database inside a pod, inside the cluster, or is it outside of the cluster?
It's in a pod inside the cluster.
Okay.
I did not test having the database as an external service and to see if that made any difference, mostly because I didn't expect it to make any difference compared to a completely non-Kubernetes test, so I didn't test that. Oh, hold on just a second. The mic is almost at you. Thank you.
You mentioned the noisy neighbor effect on cloud systems, and you also mentioned that I think you mentioned that you had done multiple runs on cloud systems. What sort of variance would you see between the runs at a maximum? Like
up to 3,000%.
Ah, okay.
If you actually look, I don't know, like SCaLE 15. I actually have a talk, that was recorded for SCaLE 15. On running databases in public cloud. Shootout in the AWS Corral. And I actually go over some of I have distribution charts for the distribution that actually led to a whole line of business for us in my old company, where we would actually run micro benchmarks on AWS to locate good instances for our customers. It was a moneymaker. Amazon actually kind of got wise to people doing that, and it stopped being quite as effective. But I mean, really, we would literally have a 30x difference between the worst performing instance and the best performing instance. And so when I was doing benchmarking on public cloud, what I actually did was a two-stage thing, right? Which is you do a whole bunch of runs, you do like 25 runs over a period of time. Because what happens is if you request a whole bunch of instances in a row, most of the clouds tend to basically stick them on the same machine. Over a period of time, and then you eliminate the outliers, which can be deceptive, right? Because you never know whether the outlier is because of a real problem or because of the cloud. And so I hate eliminating the outliers, but the outliers are so far out that I had to do it. The upside, by the way, is sometimes, if you're lucky, you can get spectacular performance from the public cloud. And on AWS, I know that's what happens is you effectively landed your instance on a brand new machine attached to a brand new storage volume that nobody else is using. But it's hard to depend on that. More questions? I have not. I did a lot of testing on Power 8 systems back in the day. Maybe Liz and I will team up and try this out on a Z series.
Once you have all the results, what's
you got a mic there. Go for it.
What's a good way to present the results so that they're easy to consume, like by people that aren't?
Well, I mean, obviously, I like those charts, right? Because I'm trying to show differences and that sort of thing. If you do a whole bunch of test runs, graphs are nice. The important thing is to always explain what the numbers are specifically showing, because there's tons of combinations that you can do for different stuff. To the extent that you can relate a benchmark workload to a real life workload that you know you're going to need to do, right? You say like, hey, we do video streaming, and so I did a bunch of sysbench and pgbench, sequential read and write tests, because that's similar to what we're going to have to do. Then that's going to be better Because, I mean, here's the thing is, right, if you do pgbench and you do a transaction test, that's going to tell you nothing or very little about that cluster's ability to handle a large, sequential activity like file sharing or something. So, yeah, beyond that, it's all, just sort of data visualization. And I tried to show here is that sometimes that's a graph, but sometimes it's other things to give people an idea.
I think that's it. So, one
wait,
more.
one more.
Yeah, let me bring this.
So you say your databases were minimally tuned?
Yes.
Do you think the results might have been different had they been, better tuned? And what database were you using for the test?
Well, so the two databases were PostgreSQL and CockroachDB. I don't think so Postgres actually has a lot of automated testing done. And so the default configuration, while it might not be great for a lot of real-world circumstances, does really well for pgbench. And so that's one of the reasons why I didn't feel like I needed to tweak it. Because one of the things that Postgres makes you tinker with is actually directly telling the database how much RAM you have available. Well, pgbench doesn't actually make use of large chunks of RAM, so it doesn't make a difference. So the CockroachDB's default configuration is a lot more tuned than, say, Postgres or MySQL are out of the box. So again, I didn't feel like I really needed to touch that. There was one setting I changed. I don't remember what it was called, but it is directly off of, they have this big page of, if you're running CockroachDB on Kubernetes, here's some settings that we recommend you change.
All right, thanks, Josh.
Thank you.
All right, cool. All right, thank you for everyone for attending today's session. It's continuous security with Kubernetes, and I'm going to be talking about some best practices for securing your DevOps pipeline for containers, and then also when it's based on Kubernetes as well, both from a developer and also from more of an infrastructure perspective.
LYZ, you said it too, right?
Mm. Let me make sure.
All right, hopefully we're going to get going now. So welcome, Chris, and thank you for coming to give a talk here on DevOps and continuous security with Kubernetes.
Right, thank you. Right, thank you everyone for coming today. I'm going to talk a little bit about Kubernetes and containers in terms of security in the CI/CD pipeline. But first off, talk about some of the business drivers as to why you would want to adopt this in your business. Just an example in the automobile industry, you know, traditionally it's a very static and planned process of releasing a new product each year. In the fall, you can predict that there be a new vehicle, new model, and every 5 years or so, maybe a complete revamp of that particular model as well. But it's a very slow innovation, very static and planned. It's really designed for global scale across the world. You know, Ford, for example, can deploy vehicles all over the place with their dealer network and different geographies. Then you have flip side of that is really Tesla, I would say, a very innovative company, and they've totally turned it upside down. No dealer network. They're able to streamline the delivery of their vehicles to their customers, and they're able to rapidly innovate. Right? The vehicle incrementally gets better, and a major reason around that is the frequency of software updates that they're able to deliver to these vehicles over the wire. And it's had a profound impact on the business because no longer is it a single transaction at the dealer lot in terms of purchasing that vehicle, but now they have add-on services, right? They can sell to their customer incremental services to maybe improve the 0 to 60 time, and it doesn't require going into the dealer network. They can deliver that update or addition over the wire. They can improve the battery efficiency to their customers as well. So really transforming the business, just like the phone industry as well, right? The iPhone turning in not just into a device that you buy, but layered services on top of that. And it's very applicable across many different industries. Right, and so IT, a lot of pressure on them to kind of evolve and transform, and that's why you're seeing this adoption of DevOps that enables the rapid frequency of updates of your applications, and that is accomplished through a change in their culture, a change in process, really automating your process of delivering software from dev into production. And then, as you see, most adopters of DevOps are leveraging open source solutions to really automate that process. But what about security, right? Security is typically an afterthought. It doesn't really align typically with moving fast, right? Security is often viewed as a bottleneck. It's viewed as process that I have to go through to get a change request approved, whether it's changing the firewall or changing the load balancer or changing the system. It is slowing down and often forgotten and often ignored, and certainly in these times we can't do that. As the move to DevOps, it's really having an impact in terms of evolving security as well. You see this movement towards microservices of breaking down the application. Now a single application may span across multiple environments. There's an increase of reliance on the network of service-to-service communication. How do you ensure that that is secure and trusted in your environment as well? It's no longer just hiding behind your firewall and your enterprise. Also, you're seeing a movement towards hybrid cloud environments. Most of our customers that we work with, we're seeing they have on-premise as well as one or more public clouds across their enterprise. So how do I have a consistent security process, tooling across these environments? How do I ensure that they're not different process per provider, you know, and exposing that to my developer, right? That's going to slow things down, and ideally I have a single consistent way of doing that across no matter where I need to deploy it for my business, whether it's at the edge, in a retail location, or in the back-end data center, or in the developer's workstation. Also, you know, of course, with the movement to cloud, multi-tenancy. How do I ensure that a business can trust the infrastructure no matter where it gets deployed? No matter whether it's sitting next to a database or a lightweight application, I want to ensure I have quality of service. I want to ensure that that infrastructure is secure. And so that's given rise to really DevSecOps, right? That's inserting security into DevOps. And security starts not in production, but it starts in development, right? And that's really a cultural change, right? You have to prioritize from a business, prioritize from a product or service perspective that security is a priority in the release and the productization. That means secure your coding practices, means continuous security testing, treating everything as code, right? Infrastructure as code. We want to enable that to be repeatable, consistent, auditable, and leveraging automation so it's consistent, and I can quickly configure and deploy across my infrastructure, no matter where it is, and I'm getting continuous feedback, right? If something's not working, if there's a security vulnerability in an image, I want to have immediate feedback that that's an issue, right? If something is down, I want to know that as well. And I can adapt, pivot, and change, and quickly release an update from dev into production in a matter of minutes rather than days or weeks. Right? So how do you do that at scale? And that's where, no pun intended, but Kubernetes is really a platform to enable not only the management and the deployment orchestration of containers across any provider, physical, virtual, private, or public cloud, but I also see it increasingly as a way to standardize your security no matter where your applications are being deployed, public or private cloud, for instance. Right? I can have a consistent set of tooling, a consistent set of processes and policies across these providers. And that allows me to move fast, right? And to ensure that I have a trusted infrastructure that I expect to be out there. And containers are a big part about moving fast, and they certainly add some benefits from a security perspective. Right? First off, I can have a bare minimum image packaged into my container so it's lightweight, has a reduced attack surface. Right? I don't have to worry about unused components being included in that container image. It also allows me to quickly respond when there is a security issue, because I can quickly go back into development, build that image, and then push it through my standard test cycle, scan it, and put it into production in a matter of minutes, typically, or minimal number of hours. Also, in terms of the quality, right? I build it once, and then I deploy anywhere, right? I'm not rebuilding or reconfiguring that application or service as it moves from dev test into production. The developer builds it, I take what the developer built, I test it as is, and I move it into production. If I need to change that due to a security issue, I go back to development and build another version. And portability, right? Able to take that image, deploy it to dev test, production, public, private cloud, physical or virtual, so I have consistency. When I have consistency, right, I can improve quality and reduce the risk. And so when it comes to a containerized environment, here are some best practices when it comes to security. One is, there's no one knob to secure everything. It's a layered security approach. There's quite a bit of different layers to this that we'll go through to provide a more and more trusted environment in your enterprise. Also, take the mindset of granting the least privileges that are necessary for your containerized microservice or application. The default typically is wide open, and so make sure that you're locking it down, and we'll talk about how. Also, reduce attack surface. So I mentioned about building an image, just the bare minimal dependencies. Keep that attack surface to a minimum, and build your images with the mindset of them being immutable. They don't change once they're built. Configurations, keep them outside of the container image. Data as well. And so let's go into some best practices. First, talk about containers. You build, you ship, and then you run, right? So when it comes to building, you have a build file, specifies the different components that go into that container image. Once it's built, you can push it into a registry that allows you to share it across dev, test, and production, or on-prem or off-prem, for example. And then I can deploy that image and instantiate it as a container instance running anywhere I have Linux operating system. My container runtime environment allows consistency because of the standardization in this industry around the image format as well as the runtime. When it comes to the image itself, it's a change in terms of a developer, what they ship and provide to their test environment or to their operations team. No longer are you just delivering your jar files, for example, in a Java application, but now they're packaging that into a container image and building it. And what's inside that container image will be the OS dependencies, right? This is the minimal footprint of your base operating system, and then the dependencies for that application from a language runtime, all the libraries or the binaries that it needs to execute. And then the application, the jar file in this case, as well. And then when I build that image, I can tag it, for instance, with a label 1.1, or version 1.2, et cetera. I can have multiple images. And because I have everything I need to run, that means I can have multiple images, multiple versions running side by side on the same host, right? I don't have to worry about how that host is configured. Also, from a security perspective, I know what versions I'll be running against as well. It's not I as the application owner. So those different layers, traditionally, different folks in your organization own those layers today. How does that translate into a container environment? So here you have operations. They can still own the OS. They'll own the base image for the operating system and can provide that as a service to their developers and their application owners. The apps or the database team can own that middle layer, the language runtimes or the database. And then the developer can own the application layer. And so these layers can come together to produce the resulting container image, right? And configurations and storage, of course, would be kept outside of that container. So we talked about treating containers as immutable. That means they don't change. So things that change, configuration or data, that's stored outside of the container image. And in Kubernetes, they provide a way to store configurations in what's called a config map. So think of this, maybe it's an IP address, it's a lab identification string that I need for my application, or maybe it's a configuration file for my application. And so that can be defined in a config map that is stored in etcd in the Kubernetes master architecture as a service. If I need to have it encrypted, Kubernetes also has what's called a secret, and I can store that value or that configuration file and have it encrypted. The data I can access via a persistent storage that Kubernetes can provision, or through like a JDBC connection, whether it's a public cloud or on-prem service. Let's take a look at an example of the config map. Maybe I have my JBoss Java application server running, and that requires an XML configuration file. Instead of storing that in my container image, I would actually define that in a text file, save it in my source code repository, version control it, and then when I define my Kubernetes application, the YAML, I would actually specify a config map that maps to this configuration file. Right? Now, when I launch and deploy my service in Kubernetes, it'll take that container image for my Java application, run it as a container instance in my cluster, and at runtime, it will define the config map based on the configuration file that I have saved in my source code repository, Git, for instance. Right, so that's separation of your configurations from the image. And also, just keep in mind, every time you build one of these images, you traditionally would add a label to version control it, easy to use, 1.1, 1.2. But be careful, because you can rebuild and reuse that label. And so when you're out in production, you can't always necessarily trust the label for uniqueness. Right? Instead, you'd have to look at what's called the digest. That has a unique ID for that image. Sometimes we see software vendors, we see development shops reusing labels, and this leads to having multiple versions out in production and trying to debug issues, wondering why things work on one system and not the other in a cluster. What about continuous building? How do I automate this process? So from a security perspective, what we're seeing is sometimes security issues aren't about changing code and inserting something. Sometimes it's about attacking the build environment and injecting a vulnerability at build time. And so a best practice is to version control your build environment. And you can do that by putting your build environment into a container image, versioning it, and then using that to build a particular version of your application. Right? And then that process would output a container image containing your application and then just the bare minimum dependencies at the app and the OS layer. It does not include the build tools, right? So it's nice and lightweight as well. Now I can go back in time and I know what version of the build environment was used to produce every version of my application. And if I archive that, I have those versions and I can redo that. But I also can inspect if there was a vulnerability inserted into my build environment as well. So best practice, and then also I can reproduce that environment consistently. So a CI/CD pipeline with Kubernetes kind of looks like this. You have your developers checking in their source code, build files, you have your operations team also doing that, you have configuration files, etc. And then it goes to the build process. It'll pull down that build image that we're talking about from your image registry and then build the resulting container image for your application. Builds it once, and then I would deploy that in my dev environment. I would deploy that in my test environment. And then I could also push that into my production environment when it's ready to be deployed. Right? That's the same consistent image across the board. I use a build image to build that container image. And in Kubernetes, I could use namespaces or individual clusters to isolate the different environments, in this case, dev, UAT, and production. But have a registry which allows you to push the images across those environments. Okay. Now, once that application is running in production, right, I have those three layers, the base OS image, I have the application dependencies, and I have my application. What if there's a security issue and there's an update to address that? Right? I, as a developer, don't need to be monitoring all three layers. I can just pay attention to my application. And you could actually automate the checking. So you could look at the dependencies and then look into the registry if there's an updated version of any of the layers that I depend on, and that could trigger an automated rebuild. So generating a new pipeline, for example, in Jenkins, to build your container image with the new, in this case, let's say there was a OS security vulnerability, there would be a new OS image available in my registry, which would trigger that rebuild, and then make that available to my test and production environments. So cascading rebuilds. Also, container registry and scanning. You know, what's inside the container matters. We talked about a container contains those 3 layers. It pulls in a lot of components. Here you have a C application, Java, Node.js, and a Perl, PHP image. And the little triangle indicates how many security notifications are for the different components that get pulled in. For example, in the second column, the Java application, the JRE, has over 60 security notifications. So not only do I need to be conscious of where I'm pulling these images and what's inside of them when I initially get that image, but I also need to have a process to continually scan and inspect these images to see if there are any new known vulnerabilities, so I can address those. And typically, to ensure that you're pulling your images from a trusted source, the first thing I see most customers in adopting containers is they set up a private registry in their data center so that they have trusted content, but they also can own the life cycle of these images as well, not defer that to a untrusted public provider. And so when you need that old version 6-12 months down the road, I know I still have that in my local registry. And you could have auditing and security in terms of who can upload and modify. In terms of addressing how do I ensure that images consistently going forward don't have security issues or vulnerabilities, I can insert a scanning process into my pipeline. So here's a Jenkins CI pipeline. You have the individual runs, the build 1, 2, 3 from bottom up. And then you see we inserted a security phase as step 4 of this process. So that will, after the image is built, it will scan that image and identify if there are any security issues. And how would I do that? You could use a variety of different tools to scan your images. One tool that's an open source solution is called OpenSCAP. That allows you to scan the image for known vulnerabilities, so checks based on the RPM versioning. And then secondly, you could scan that to see if it conforms with your security policy. So you can define a security policy, maybe it's the minimum password length, such as this example, and if that image doesn't meet that standard, it will flag it and alert you in one of the reports. It will generate remediation scripts in Ansible, so you can rectify that issue. And then also, you have an audit log as well, in case you need to show that for reporting purposes. So there are a lot of tools out there, but OpenSCAP is one such tool. In Kubernetes, you know, how do you enable and automate your CI/CD pipeline? A lot of early adopters of DevOps and CI/CD pipelines, they customized and wrote with scripts. Now there's a lot of tools out there. Kubernetes certainly enables a lot of automation out of the box that you can take advantage of. And a big difference here, as we've been talking about, is that you build your container image once and you push it all the way through production. And so how do I, when there is a security vulnerability in my production environment, I'm not going to go and patch SSH into my box and patch or upgrade the version out on my production system directly. Traditionally, you may do that today because it takes 2 weeks to push a new version to go from dev into production. But with this highly automated CI/CD pipeline, Right now I can go back to developers and always have them address that with a new version release. And instead of SSHing into my box, I can leverage one of these continuous delivery or continuous deployment mechanisms in Kubernetes. There are different models. I could do a recreate, I can do a rolling update, a blue-green, or for experimentation, I'll do an A/B testing with canaries as a developer. The recreate, that basically is the simplest model. You have version 1 of your service out in production, and to go to version 2 with that new security fix, I just take down version 1, I have some downtime, and I deploy version 2. Very simple, don't have to interact with the developers. It's very easy in that regard. What if I have requirements to keep the application or service up all the time with zero downtime? Then I might want to look at these other options. One is rolling up. You have 3 instances or 3 pods of your application out in the cluster. It will upgrade each one individually until you get to 100%. And you could stop and roll back at any point. And that allows me to have zero downtime, but it requires my application to be able to handle 2 different versions in production at the same time, right? And so I need to make sure my database schema and my application are aligned for that. Thirdly, the blue-green, right? I have my version 1 out there in my blue environment. It's time to upgrade to version 2 with that new security update. I can just flip the traffic using the selector in a Kubernetes service to route the traffic from version 1 over to version 2, let the version 1 traffic die down, zero downtime. I also can quickly revert back to version 1 because I didn't bring it down in case there's an issue. And so there's a little bit more comfort knowing that I can revert back without any changes, and it continues to be just as I left it. And then lastly, A/B testing. So I'm going to go a little more detail so you see an example of this one. But this is commonly used to accelerate the delivery of updates in Kubernetes. You enable your developers to experiment, try things out. If there's a security issue, they can test out that new version quickly and deploy with confidence before they roll out to everyone in production. So in this example, on the left side, I have version A, and I want to experiment and try out a new recommendation engine for my mobile application. Here you can see it's recommending a few different products on the right side. So this could also include a security update. So my existing version A is out in production. It gets 100% of the traffic. I see the conversion rate is 25%, so I'm getting that continuous feedback. I'm doing that by setting up a service, a Kubernetes service that front ends this version A. And I've defined a selector of demo in version A that routes all the traffic over to version A. And I have a third party tool tracking the conversion rate. There's a security issue, et cetera. I want to try out version B. What I can do is put that through testing. I go ahead and deploy that with the label of app equals demo, version equals B. And I can update the selector so that it starts routing some of the traffic over to version B, right? In this case, it's just I've only deployed 1 pod, whereas version A has 3 pods, so it's going to get 25% of the traffic just based on the number of pods. If you need finer granularity of routing your traffic, that's when you want to look at something like a service mesh, like Istio, where you can do, I want 1%, 2% of my traffic to go to this particular version, right? But this is a simpler model without the additional complexity. And now that I have confidence that security update in version B is working well because it improved the conversion rate as well with that new recommendation engine, I'm going to route all that traffic to version B, and I just add the updated selector with the version B label. And that's all in using Kubernetes, right? Another thing I may have to do is quickly move from one database to another database. Right? Maybe it's as I move from dev into production, or I need to move from one version to another version. How do I do that? Maybe I'm addressing a security issue. So in Kubernetes, they provide some ease of use around that. Is on the left, I have a development database, and on the right, I have a production with different IP address. And what I can do is I can deploy my web app into Kubernetes as a pod. It'll pull down the image. It's running. And I don't want to hard code that image with an IP address. Right? Otherwise, I would have downtime if I want to change it. And it's just a bad practice. It's not a mutable image either. And so in Kubernetes, what you can do is you can set up a service of cluster IP type and define, in this case, it's in the front end of MongoDB. And I want to leverage that service to route traffic to whatever database I want behind there. So initially, I want the red database. And so I define an endpoint for that service with the IP address of the external database. In this case, it's on a cloud, public cloud service that's running outside of Kubernetes. Now, maybe there's a security issue. I need to switch over to the blue one. And instead of bringing down my image or my instance and changing it, I can actually just update the object in Kubernetes, the endpoint, with the blue IP address. Right? So minimize downtime. I can have a static connection string in my image, probably defined as a config map as well, to make it easy to change if I do need to. And that allows me to be able to move fast and address perhaps a security issue at the database level. If you need to use a URI, you could also do that. A lot of cloud services require that. Right. What about addressing a security issue due to maybe a schema change? Right? How could I manage that? Also, a lot of people just ask, how do I do DevOps with databases that are running inside Kubernetes? And this is an example where you have version 1 of the schema in production, version 2 in test, and a subsequent version in development. And I'm going to push those through the pipeline. What you can do is you can use a tool such as Flyway. It's an open source tool to do version schema control. And what you do is you define your schema change, like in your SQL file here. You version control it. And then you create a Flyway container image with that SQL change and the Flyway application, right? And I version it, and I call it, in this case, Flyway MyDB version 2, so version 2 of my schema. Right? This is a very simple model of how to do it. I could use config maps as well. And now that I have that image with Flyway in my database schema, version 2 defined, I can then roll that out quickly into Kubernetes. So I have version 1 of my PostgreSQL database running. There's a security issue, requires a schema change. What I do is I run and create a Kubernetes job. So this is a way of deploying and running one container instance one time. In this case, it's going to run the Flyway application. It's going to pull down the Flyway version 2 image. It has the username password to connect to this database over JDBC. Once it starts, it immediately connects to the database, and it has the SQL script that we saw earlier to upgrade the schema to version 2. Right? So typically, if I want to deploy go from version 1 to version 2 of my application, I would first upgrade the schema of my database to make it not only compatible with version 2 of my application, but also version 1, have some backwards compatibility. And then you could drop that, you know, however many N-1 versions you want to maintain backwards compatibility. Okay. And now I have version 2 of my database. So that's updating schema changes quickly that may be associated with a security issue. Now, we talked about a continuous feedback loop. As you move to a containerized environment, you need to be aware of kind of the different tools you have available to see what's going on in your environment. You know, traditionally you have access to your host level information, CPU memory, et cetera. And so the node exporter is a tool there. What about the container level, right? So you can get metrics from the kubelet, which is the process that runs on the nodes in the Kubernetes cluster. This is a C-advisor, so it provides different metrics about each pod and container, what they're consuming. Also, there's metrics for the Kubernetes cluster itself. And then at the microservice level, you're probably going to be looking at, from a development perspective, adopting a service mesh as you get more sophisticated applications so that you can manage at a finer granular level the traffic from service to service, as well as controlling mutual TLS between service to service so you know that they're trusted. Also potentially routing traffic from outside in, and also being able to have observability. So using a tool like Jaeger to get visibility into how much traffic is going from one service to another, and then also using Istio or Service Mesh to control that traffic, right? Routing the traffic. If something's not responding, you know, give up after 3 tries, wait 5 minutes, then try again rather than bringing down your entire infrastructure. Also, the ability to mirror traffic from production into tests so I can experiment and try things out. Right, so those are some considerations. Now at the infrastructure level, you know, here's the Kubernetes architecture. And everything in blue, you know, really comes with Kubernetes. But in order to run Kubernetes, you need some additional components. Right? You need a Linux operating system on your nodes to run those containers. You need a container runtime as well, right? Like CRI-O. And you need a network and DNS service. You need storage if you want to have persistence. And you need typically a dashboard or management console, monitoring, logging, security, and a registry to store your images. Right? And so some of the best practices from a security perspective around your Kubernetes cluster, just in general, is don't run your container images as root. Right? A lot of new users are not aware that container images run by default as root. You have to specify in that build file a user for it to run as. Otherwise, it just defaults to root. Right? So best practice also is in your cluster, disable containers from running as root. And we'll talk about how that can be done in a minute. Also, limit the Linux capabilities. If you are going to run as root, you can pare down what that user has the ability to do on a Linux system. Limit SSH access. You know, use namespaces for isolating your dev, test, and production environment, or use individual clusters. You know, define the resource quotas so you don't have a noisy neighbor problem. You know, if you have some sort of attack that could bring down other applications that live side by side. Enable logging so you can have an audit trail. Right? Apply security errata not only to the container image, as we talked about in the CI/CD pipeline, but also to the nodes in the cluster. And then pod security policies, I'll talk about in just a second, audit policies. And you know, if you are going to run unprivileged containers, run them as read-only. So a tool like, you can use Podman, for instance, to run as read-only. And we're running a little bit out of time. So I'm going to quickly just show you from an infrastructure perspective. One is in Kubernetes, you can use a pod security policy to restrict and limit what can run on a node in a cluster. So if you don't want to run anything as root, you can define in a pod security policy to be restrictive. And there are a lot of other capabilities. Also, you can enable an audit policy in Kubernetes as well. So you have an audit trail of the different activities, the API requests that are going on in your cluster. And it's important to understand kind of the Kubernetes API server is really the heart of Kubernetes. All the requests are going through this API service, and you have HTTPS into the API. You have some authentication. Then they're seeing what authorization that user has. And then there's what's called an admission controller, right? This can mutate request based on your policy, or it could reject a request based on your policy, so it doesn't get sent out to the cluster, right? So pod security policies, audit policies, et cetera, they're all tied in to the Kubernetes API server and the admission controller. And then lastly, you can also define network policy, right? This allows you to restrict the communication of pods in your cluster across different namespaces or within the namespace, right? If you want to lock that down, define a network policy in your with your application and restrict network traffic. Okay. So we're almost out of time. I just want to talk about some additional areas to explore beyond this. There's some exciting projects that are being layered on top in the Kubernetes ecosystem. Kubernetes is really driving towards being a platform that can run any application, AI/ML, virtual machine, a container base. And so KubeVirt is a project to bring virtual machines to Kubernetes. Also, once you have applications containerized, really the challenge is how do you automate the operations of those services? So I have that same experience I would get from using Salesforce or an Amazon service. Right? I don't have to worry about security updates. I don't have to worry about scaling up or scaling down. Right? An operator is a way to take your manual run book for operating a custom service or a third-party service like MongoDB and automating those day-to-day operations for your team. That way, the expert can define it once. It could be an Ansible or Go, and deployed as an operator on top of Kubernetes, essentially automating that for you from a security perspective adds a lot of value in terms of automating that as well. Serverless. You can have serverless applications using Knative, for instance. We talked about some of the benefits from a security perspective for a service mesh. Istio is one project out there. And then having a CI/CD pipeline defined in a Kubernetes native way, that's where the Tecton project is working on, is automating pipeline in a Kubernetes YAML-friendly way and defining that and having that version controlled and easy to manage when you are leveraging Kubernetes. Right. Okay, well, that's out of time, and I want to thank everyone for attending. Here's my contact info. Feel free to reach out, LinkedIn, my Red Hat email address as well. Also be out in the hallway if you want to discuss anything. I know we're a little bit over, so I'll be shutting down pretty quickly. Thank you so much.
Thanks, Chris.
Thanks, everyone. We'll see you tomorrow morning. We'll be starting off at 11:30 with using operators in order to manage databases on Kubernetes.
And thanks again for stepping in.
Oh, yeah, no worries. I live in downtown, so that worked out.
Oh, nice. Okay.
Yeah. Thanks, Josh.
Thank you. I'm glad you could make it.
Oh, yeah.
bigger turnout than I expected. That was nice.
Yeah, Fridays are nice.